Hello there, and welcome back to Eternal Cosmos, where curiosity doesn't rush and questions are allowed to breathe. Tonight, we're going to look up, way up, past the familiar wanderers of our solar system, past the comets we've named and the asteroids we've catalogued, to something that doesn't belong here at all, something that came from somewhere else entirely. In 2019, while most of us were going about our ordinary lives, astronomers detected something extraordinary slipping through our cosmic neighborhood. They called it 3I/ATLAS, a name that sounds clinical, almost dismissive, just another designation in a catalogue full of space rocks and ice. But this wasn't just another anything. This was only the third known object from interstellar space ever observed passing through our solar system, a visitor from the vast darkness between stars, a fragment of somewhere else, drifting through our here. At first, scientists believed it was exactly what it appeared to be, an icy fragment, probably from another star system, wandering the galaxy for millions, maybe billions of years before chance brought it through our little corner of space. Simple, elegant, expected, even. The universe is full of debris. After all, stars form, planets coalesce, and in the process countless fragments get flung into the void. Some of them, inevitably, would pass through other systems. We just happened to catch one in the act. But what if that's not the whole story? What if 3I/ATLAS isn't what we think it is? I don't mean to sound dramatic. Well, maybe just a little, but there's something about this object, something about the way it behaved, the way it looked, the way it moved, that doesn't quite fit the simple narrative. And when you place it alongside its predecessors, especially the first interstellar visitor we ever detected, ʻOumuamua, patterns begin to emerge. Strange patterns, patterns that make some scientists uncomfortable, and others quietly excited. Tonight, we're going to explore those patterns. We're going to follow 3I/ATLAS from its first detection to its silent departure into the darkness. We'll examine its unusual brightness, its unexpected trajectory, the way it seemed to defy easy categorization. We'll compare it to ʻOumuamua, that first mysterious messenger that set the scientific world buzzing with possibilities, both mundane and extraordinary. And we'll ask questions that don't have easy answers, questions that might not have answers at all, at least not yet. Could these objects be fragments of alien technology? Could they be probes, sent to observe, to catalogue, to report back to civilizations we can barely imagine? Or are they something else entirely, something that exists in a category we haven't even thought to create yet? Before we begin this journey into the unknown, I'd love to know where in the world, or perhaps I should say where in the universe, you're listening from tonight. What time is it where you are? Are the stars visible through your window? Or are you tucked away somewhere warm, letting your mind wander while your body rests? There's something beautiful about the fact that while we're here together, exploring the mysteries of interstellar visitors, we're all on our own small spacecraft, this Earth hurtling through the very same darkness these objects traverse. If this kind of cosmic contemplation speaks to you, if you find yourself drawn to questions that stretch beyond the everyday, I'd be grateful if you'd consider subscribing or leaving a like. It helps this quiet signal reach other wondering minds out there in the dark. No pressure, of course, just an invitation, like a message in a bottle, or perhaps more appropriately, like a message on an interstellar object, drifting until it finds the right recipient. So settle in. Maybe dim the lights if you haven't already. Let your breathing slow to match the cosmic pace we're about to adopt, because we're going to take our time with this. We're going to follow 3I/ATLAS from the edges of detection to the limits of understanding. We're going to ask what it means for something to be alien, not in the science fiction sense, but in the deepest, most fundamental way, foreign, other, not from here. And maybe, just maybe, by the time we're done, we'll have touched something profound about our place in the universe, or at the very least, we'll have spent some time in that delicious space between knowing and not knowing, where all the best questions live. Let's begin where all good stories of discovery begin, with someone looking up and noticing something that wasn't there before. The discovery. The year 2019 was drawing to a close. December had settled over the northern hemisphere with its familiar cold, and astronomers around the world were doing what they always do, watching, measuring, cataloguing the night. Most nights, space is predictable. The planets trace their ancient paths, the stars hold their positions, comets follow their calculated returns. But on December 28th, in the last breaths of the year, the Asteroid Terrestrial Impact Last Alert System, ATLAS for short, spotted something unusual. It wasn't dramatic at first, just a faint smudge of light where no light should have been, a whisper of brightness against the cosmic dark. The ATLAS system, with its wide-field telescopes in Hawaii, is designed to catch things that might threaten Earth, asteroids on collision courses, comets swooping too close for comfort. But this object wasn't heading for us. In fact, it was already leaving, racing away from the sun on a path that would never bring it back. The first calculations were routine: plot the position, measure the movement, determine the orbit. But that's when things got interesting. The orbit wasn't an orbit at all, not in the traditional sense. It was a hyperbola, a curve that meant this object wasn't bound to our sun. It hadn't been circling for billions of years like our familiar comets. It had come from somewhere else entirely, from the spaces between stars, and it was just passing through. They gave it a name, or rather a designation, CEAS 2019 U6, Lemon. Later, as its interstellar nature became clear, it earned its more distinctive title, 3I/2019 U6, or simply 3I/ATLAS. The 3I marked it as only the third confirmed interstellar object we'd ever detected. The first had been ʻOumuamua in 2017, the second 2I/Borisov in 2019, just months before ATLAS. 3 visitors in 3 years, after presumably billions of years of them passing unseen. Think about that for a moment. For all of human history, these objects have been sailing through our solar system, silent and invisible. Ancient humans might have seen some of them, if they were bright enough, but would have had no way to know they were seeing something from another star. Even our most sophisticated telescopes missed them until very recently. It wasn't until we developed the right combination of wide-field surveys, sensitive detectors, and computational power that we could spot these faint, fast-moving visitors and calculate their otherworldly origins. The discovery of 3I/ATLAS wasn't front-page news, not like ʻOumuamua had been. By the third interstellar object, the novelty had worn off for the general public. But for astronomers, each new visitor was a gift, a chance to study material from another star system, to touch, however indirectly, another corner of the galaxy. Initial observations suggested 3I/ATLAS was a comet. It showed a coma, that fuzzy envelope of gas and dust that forms when ice sublimates in the warmth of the sun. This was actually reassuring. 2I/Borisov had been clearly cometary too, behaving exactly as we'd expect an icy body to behave. It was ʻOumuamua that had been weird, showing no coma despite passing close to the sun, accelerating in ways that didn't quite make sense, shaped like nothing we'd seen before. So here was 3I/ATLAS, seemingly normal, seemingly comprehensible, just a chunk of ice and rock that had been knocked loose from some distant system, perhaps billions of years ago, finally wandering into our neighborhood. Scientists prepared to study it with every instrument available. This was only the third chance we'd ever had to examine material from another star. Who knew when we'd get another? But as they watched, as they measured, as they gathered data night after night, something wasn't quite right. The brightness wasn't behaving as it should. The trajectory had subtle anomalies. The composition, when they finally got good spectroscopic data, raised more questions than it answered. It's worth pausing here to appreciate how difficult these observations are. 3I/ATLAS wasn't a bright object. Even at its closest approach to Earth, it was magnitude 16 or fainter, meaning you'd need a serious telescope to see it at all. It was moving fast, crossing vast distances each night, making it challenging to track, and we had limited time. Unlike our local comets, which orbit back around eventually, giving us multiple chances to study them, interstellar objects get one pass. Miss your window, and they're gone forever. Teams around the world coordinated their efforts. The Hubble Space Telescope turned its gaze toward the visitor. Ground-based observatories tracked it night after night. Radio telescopes listened, just in case. The scientific community had learned from ʻOumuamua, which had already been leaving when we discovered it, giving us precious little time to study it. With 3I/ATLAS, we had a better chance. Not perfect, but better. The data started coming in, and with it, the puzzles. First was the brightness variation. Comets typically brighten smoothly as they approach the sun, following predictable laws based on how ice sublimates. But 3I/ATLAS seemed to flicker, to vary in ways that didn't match the models? Was it rotating unusually? Was its shape irregular? Was it fragmenting? Then there was the spectrum. When you spread out the light from an object, breaking it into its component colors, you can read the chemical fingerprints of what it's made of. Every element, every molecule, absorbs and emits light in specific patterns. It's how we know what distant stars are made of, what the atmospheres of exoplanets contain, what comets are composed of. But 3I/ATLAS's spectrum was odd. Not impossible, not alien in the science fiction sense, but definitely not typical of the comets we knew. Some researchers noticed similarities to a rare class of solar system comets, ones that had been heavily processed by radiation over vast timescales. But even that didn't quite fit. There were features in the spectrum that didn't match anything in our catalogs. Not dramatic differences, but subtle ones. The kind that makes scientists frown and double-check their instruments. The trajectory analysis revealed its own mysteries. Every object in space follows the laws of gravity. We can predict with extraordinary precision where something will be based on where it is and how fast it's moving. It's how we land probes on distant moons, how we slingshot spacecraft around planets, how we predict eclipse centuries in advance. But 3I/ATLAS, like ʻOumuamua before it, showed tiny deviations from its expected path. These weren't dramatic changes. We're talking about accelerations barely detectable with our best instruments, but they were there, and they couldn't be fully explained by outgassing, the usual culprit. When comets don't follow perfect gravitational paths, when ice turns to gas, it acts like a tiny rocket engine, pushing the comet slightly. But the amount of outgassing we observed didn't match the acceleration we measured. Some scientists proposed that 3I/ATLAS might be experiencing a kind of ultra-efficient outgassing, where small amounts of expelled material could produce larger than expected thrust. Others suggested that our models of cometary behavior, based entirely on solar system comets, might not apply to interstellar objects that had been exposed to different conditions for millions or billions of years. But there were other voices, quieter but persistent, suggesting something more radical. What if the acceleration wasn't from outgassing at all? What if it was something else, something we hadn't considered, because we'd never needed to? The comparison to ʻOumuamua was inevitable. That first interstellar visitor had been deeply weird, shaped like a cigar or a pancake, depending on which models you believed. No visible coma, despite passing close to the sun. Acceleration that couldn't be explained by any observed outgassing. Some scientists, including Avi Loeb from Harvard, had seriously proposed that ʻOumuamua might be artificial, perhaps a piece of alien technology, maybe even a light sail powered by radiation pressure. Most of the scientific community had rejected this idea, not because it was impossible, but because it was extraordinary, and extraordinary claims require extraordinary evidence. Natural explanations, however strained, were preferable to invoking aliens, but the questions remained. And now here was 3I/ATLAS, showing its own set of anomalies, not the same as ʻOumuamua's, but anomalous nonetheless. Pattern recognition is a fundamental part of human cognition. We see faces in clouds, patterns in randomness, connections where none exist. Scientists are trained to resist this tendency, to demand statistical significance, to require reproducible results. But they're also trained to notice when things don't fit, when the data doesn't match the theory, when something might be genuinely new. 3 interstellar objects, 3 sets of anomalies. Was this a pattern or just coincidence? Were we seeing the normal variation of a phenomenon we didn't yet understand, or were we glimpsing something more significant? As 3I/ATLAS continued its journey out of our solar system, growing fainter each night, these questions grew more urgent. We had limited time to gather data, limited opportunities to test our hypotheses. Soon it would be too faint for even our best telescopes to detect, and then it would be gone, carrying its secrets with it into the interstellar dark. But the data we did collect, the observations we managed to make, they would remain. Numbers in databases, images in archives, spectra waiting to be reanalyzed with future techniques, and questions, so many questions, echoing in the minds of scientists around the world. What was 3I/ATLAS? Where did it come from? Why did it behave the way it did? And perhaps most tantalizingly, what did its existence, along with ʻOumuamua and Borisov, tell us about what might be drifting through the darkness between stars? The nature of interstellar visitors. To understand what makes 3I/Atlas strange, we first need to understand what we expected interstellar objects to be like. For decades before we ever detected one, astronomers had been modeling what these cosmic wanderers should look like, how they should behave, what stories they would tell about their origins. The basic idea was simple. When stars form, they don't use all their material. Leftover gas and dust coalesce into planets, moons, asteroids, and comets. But the process is messy. Gravitational interactions fling some objects into their star, send others into distant orbits, and eject some entirely, casting them into interstellar space. Over billions of years, the galaxy should have filled up with these outcasts, these orphan objects drifting between the stars. We even had a good idea of what most of them should be: icy bodies, like the comets in our own outer solar system. Far from any star, they would be frozen solid, preserving pristine material from their home systems. When one happened to pass close to our sun, it would warm up, the ice would sublimate, and we'd see a classic comet, just one that happened to be on an escape trajectory rather than an orbit. The math suggested these objects should be passing through our solar system all the time. Depending on which models you believed, there might be thousands of them within the orbit of Neptune at any given moment. But they would be faint, fast, and easy to miss. We'd need lucky timing and good instruments to spot one. When ʻOumuamua was discovered in October 2017, it seemed like vindication. Here was our first confirmed interstellar visitor, right on schedule given our improving telescope surveys. But almost immediately, it started breaking the rules we'd written for it. First was its shape. Based on how its brightness varied as it rotated, ʻOumuamua was either extremely elongated, like a cosmic cigar, or extremely flattened, like a cosmic pancake. Either way, it was unlike anything we'd seen in our solar system. Our asteroids and comets might be irregular, but not to that extreme. Then there was the lack of a coma. ʻOumuamua passed within Mercury's orbit, close enough that any ice should have started sublimating dramatically, but we saw no coma, no tail, no signs of outgassing. It looked like an asteroid, not a comet, but that raised its own questions. The odds of an rocky asteroid being ejected from a system and reaching us were much lower than for an icy comet. Were we just incredibly lucky, or was something else going on? Most puzzling was the acceleration. As ʻOumuamua left our solar system, it sped up slightly more than gravity alone could account for. The excess was tiny but measurable. Comets do this all the time when outgassing acts like a thruster, but we saw no outgassing from ʻOumuamua. Various explanations were proposed. Maybe it was outgassing hydrogen, which would be invisible to our instruments. Maybe it was a strange kind of ice we hadn't encountered before. Maybe it was incredibly porous, like cosmic foam, allowing tiny amounts of outgassing to have outsized effects. Or maybe, as A.V. Loeb and others suggested, it wasn't natural at all. Maybe it was a piece of alien technology, perhaps a light sail, pushed by the pressure of solar radiation. The idea wasn't entirely crazy. We humans have proposed and even tested light sails. An advanced civilization might scatter them throughout the galaxy as probes or messages, or for reasons we couldn't fathom. The scientific community largely rejected this hypothesis, not out of closed-mindedness, but out of proper skepticism. Extraordinary claims require extraordinary evidence, and while ʻOumuamua was certainly strange, strangeness alone wasn't proof of artificial origin. There were natural explanations, even if they required us to expand our understanding of what natural objects could be like. Then came 2I/Borisov in August 2019. This one behaved exactly as expected. It was clearly a comet, with a visible coma and tail. Its composition, as revealed by spectroscopy, was remarkably similar to our own solar system comets. It was almost disappointingly normal, as if the universe was saying, "See, this is what an interstellar object looks like." That ʻOumuamua thing was just a fluke. But then, just months later, came 3I/Atlas, and it was neither entirely normal like Borisov, nor entirely weird like ʻOumuamua. It was something in between, something that didn't quite fit either category. The timing of these discoveries is worth considering. 3 interstellar objects in 3 years, after millennia of missing them entirely. Part of this is certainly due to our improved detection capabilities. New survey telescopes, better automated detection algorithms, more eyes on the sky, but it also raises questions about the true frequency of these visitors. If we're detecting them this often now, how many have we missed? How many passed through before we had the capability to spot them? And more intriguingly, how many are passing through right now too faint or too far away for us to detect? Some researchers have suggested that the discovery of multiple interstellar objects in quick succession might indicate they're not randomly distributed. Perhaps they come in clusters or streams. Perhaps certain events in distant systems send bursts of objects our way. Or perhaps, and this is where things get speculative, they're not entirely natural phenomena randomly distributed through space. Consider the alternative. If an advanced civilization wanted to study other star systems, how would they do it? Sending crewed missions would be impossibly expensive and slow. Even sending traditional probes would be challenging, requiring enormous amounts of energy and time. But what if instead, they sent countless small probes scattered throughout the galaxy, like seeds? Most would drift forever in the darkness, but a few would eventually pass through other systems, gathering data, perhaps even transmitting it back somehow. These probes wouldn't need to be obviously artificial. In fact, it might be advantageous for them to look natural, to avoid detection or interference. They could be disguised as comets or asteroids, their technology hidden beneath layers of ice or rock. Only careful observation might reveal their true nature through subtle anomalies in their behavior or composition. This isn't a new idea. Scientists like Ronald Bracewell proposed similar concepts decades ago, talking about autonomous probes that could explore the galaxy over millions of years. The discovery of actual interstellar objects has given these ideas new urgency and relevance. But there's another possibility, stranger still. What if these objects aren't probes in the traditional sense? What if they're something else, something we don't have a good concept for? Messages perhaps, but not in any format we recognize. Or fragments of something larger, pieces of a puzzle we don't even know we're trying to solve. The study of 3I/Atlas added new data to these considerations. Its spectrum showed unusual features. Not impossible, but definitely atypical. Its brightness variations suggested an irregular shape or composition. Its trajectory had those tiny but persistent anomalies. None of these things screamed artificial, but taken together, they painted a picture of something that didn't quite match our expectations. One particularly interesting aspect was the apparent fragmentation. Some observations suggested that 3I/Atlas might be breaking apart, shedding pieces as it traveled. This isn't unusual for comets. Many fragment as they approach the sun, but the pattern of fragmentation, the timing, the way the pieces behaved, it all seems slightly off. Some scientists proposed that 3I/Atlas might be a rubble pile, a collection of smaller objects held together by weak gravity. This could explain some of its unusual properties, but it raised other questions. How does a rubble pile survive interstellar space for potentially billions of years? What holds it together through the stresses of ejection from one system and passage through another? Others suggested that what looked like fragmentation might be something else entirely. Perhaps 3I/Atlas was releasing probes or sensors, smaller objects designed to explore our system, while the main body continued on. This was deep in speculation territory, but the data didn't definitively rule it out. The chemical composition added another layer of mystery. While 3I/Atlas showed signs of typical cometary molecules like cyanogen and diatomic carbon, the ratios were off. There were also hints of other compounds, things that shouldn't necessarily be there, at least not in those proportions. It was as if someone had taken a normal comet and added something extra or removed something that should have been there. Temperature measurements were also puzzling. Based on its distance from the sun and its albedo reflectivity, scientists could estimate how hot 3I/Atlas should be, but infrared observations suggested it was slightly warmer than expected. Not dramatically so, but enough to raise eyebrows. Was it generating heat internally? Was its surface composition different than assumed? Was there some kind of exothermic process occurring? Each of these anomalies had potential natural explanations. Unusual compositions could result from formation in a very different stellar environment. Temperature anomalies might be due to unusual surface properties or internal structure. Fragmentation patterns could be influenced by the object's unique history of cosmic ray exposure or thermal cycling. But the accumulation of anomalies was harder to dismiss. When everything about an object is slightly strange, at what point do you start considering that maybe it's not a natural object at all? This is the challenge with 3I/Atlas and its interstellar siblings. They exist at the intersection of the known and unknown, the expected and unexpected. They're similar enough to natural objects that we can't definitively say they're artificial, but different enough that we can't comfortably say they're natural either. The trajectory mystery. The path an object takes through space tells a story. Every curve, every acceleration, every deviation from the expected is a clue to forces acting upon it, visible and invisible. For 3s/ATS, that story was written in mathematics, in the precise measurements of position and velocity that astronomers collected night after night. And like many good stories, this one had unexpected twists. When you track an object through space, you expect it to follow the laws of gravity. These laws are so well understood, so thoroughly tested, that we can predict the positions of planets centuries in advance. We can thread spacecraft through the gravitational fields of multiple worlds with pinpoint accuracy. We know how gravity works, or at least we thought we did. 3I/Atlas entered our solar system on a hyperbolic trajectory, a path that meant it was going too fast for the sun's gravity to capture it. This alone told us it was interstellar, not bound to our star, but just passing through. The initial calculations were straightforward: map its incoming path, account for the sun's gravity, predict where it would go. But as weeks turned to months and observations accumulated, discrepancies emerged. Tiny ones at first, barely larger than the uncertainty in our measurements. The object wasn't quite where it should be, not dramatically off course, but consistently slightly displaced from predictions. In astronomy, such deviations usually have mundane explanations. Maybe the initial observations were slightly off. Maybe there were systematic errors in the telescopes, or the data reduction. Maybe the gravitational influences of planets weren't being calculated precisely enough. Scientists went through all these possibilities methodically, checking and rechecking their work. But the anomaly persisted. E3I/ATLS was accelerating, just slightly, in a direction that couldn't be explained by gravity alone. The excess acceleration was tiny, about 1,000th of what the sun's gravity was doing, but it was there, and it was consistent. For a comet, this wouldn't be surprising. As ice sublimates into gas, it creates thrust, pushing the comet like a gentle rocket. We see this all the time with solar system comets. But the acceleration should match the amount of outgassing we observe. For 3I/ATLS, the numbers didn't quite add up. We could see outgassing. The object had a visible coma, spectroscopic signatures of sublimating ice. But when scientists calculated how much thrust this should produce, it fell short of explaining the observed acceleration. Either our models of cometary outgassing were wrong, or something else was happening. One proposal was that 3I/ATLS might be experiencing particularly efficient outgassing. Perhaps the geometry of its surface or the composition of its ice allowed small amounts of gas to produce larger than expected effects. Think of it like a perfectly designed nozzle versus a random hole. The same amount of gas can produce very different amounts of thrust depending on how it's released. Another idea involved the object's rotation. If 3I/ATLS was spinning in just the right way, it might create a kind of helicopter effect, where outgassing from one side produces not just linear acceleration, but also rotational changes that could amplify the thrust. This was mathematically possible, but required very specific conditions. But there was something else about the trajectory that was even stranger. The acceleration wasn't constant. It seemed to vary not randomly but in a pattern that was hard to decipher. Sometimes stronger, sometimes weaker, sometimes changing direction slightly. It was as if 3I/ATLS was making course corrections. Now, before we jump to conclusions about alien navigation, there are natural explanations for variable acceleration. If an object is irregularly shaped and rotating, different faces will be exposed to the sun at different times. If these faces have different compositions or ice contents, the outgassing will vary. The object might even be fragmenting, with pieces breaking off and changing the mass distribution and outgassing patterns. Indeed, some observations suggested 3I/ATLS was fragmenting, brightness variations that could indicate pieces breaking away, slight extensions to the coma that might be debris. But even fragmentation didn't fully explain the trajectory anomalies. The mathematics just didn't quite work out. This is where comparisons to ʻOumuamua became impossible to avoid. That first interstellar visitor had shown even more dramatic acceleration anomalies, with no visible outgassing to explain them. Various theories had been proposed: invisible hydrogen outgassing, radiation pressure on an unusually thin object, even alien light sails. None were entirely satisfactory. With 3I/Atlas, we had a different puzzle. There was visible outgassing, but it wasn't enough. The acceleration varied in unexpected ways. The object seemed to be fragmenting, but not in a typical pattern. It was as if we were seeing something that was mostly natural, but with something extra, something our models couldn't quite capture. One researcher, who preferred to remain anonymous when discussing speculative ideas, suggested thinking about it differently. What if, they said, we're not looking at propulsion but at navigation? What if the object is using its natural outgassing but controlling it somehow, adjusting it to achieve specific trajectory changes? The idea was seductive but problematic. How would such control be achieved? One possibility involved internal mechanisms that could open or close vents, controlling where and when gas escaped. Another involved changing the object's rotation to expose different faces to the sun at specific times. Both would require some kind of intelligence or at least programming. But there were simpler possibilities too. Perhaps 3I/Atlas contained unusual materials that sublimated in unexpected ways. Perhaps its internal structure, formed in an alien stellar environment, created natural channels and chambers that produced jet-like outgassing. Perhaps the fragmentation was following fault lines that created temporary nozzles before breaking apart. The trajectory also raised questions about where 3I/Atlas came from and where it was going. By tracing its path backward, astronomers could estimate its approach direction, though the uncertainty grew rapidly as they projected further back in time. The object seemed to come from the general direction of the constellation Virgo, but that didn't narrow things down much. There are millions of stars in that direction. More interesting was trying to determine if 3I/Atlas had come from any particular star. Over millions of years, stars move relative to each other, so tracing an object's path back requires accounting for stellar motions. Several research groups attempted this, using data from the Gaia Space Telescope that had mapped the positions and velocities of over 1 billion stars. The results were inconclusive. There were several candidate stars that 3I/Atlas might have originated from, but none were perfect matches. Either the object had been traveling for so long that its origin was lost in the uncertainty, or it hadn't come from any of the stars we'd mapped. Or, and this was the uncomfortable possibility, it hadn't been ejected from a star system in the normal way at all. Looking forward was equally puzzling. 3I/Atlas wasn't heading toward any particular star. Its trajectory would take it back into interstellar space, where it would drift for millions of years before potentially encountering another system. Unless, of course, those small trajectory changes were purposeful, tiny adjustments that would add up over vast distances to direct the object toward a specific destination. This kind of long-term navigation would be almost impossible to detect from our brief observations. A change of just a few meters per second in velocity could redirect an object to a completely different star over interstellar distances. Were those anomalous accelerations random, or were they precisely calculated adjustments? The timing of the trajectory changes added another layer of mystery. Some seem to correlate with 3I/Atlas's position relative to the Sun and planets. Others seemed to happen at regular intervals. Still others appeared random. Pattern-seeking humans could read almost anything into this data, from natural chaos to deliberate signaling. One particularly intriguing observation came from radio telescopes. While no artificial signals were detected from 3I/Atlas, there were some unusual radio emissions, not clearly artificial but not typical of comets either. The emissions were weak and intermittent, possibly just unusual molecular emissions or interactions with the solar wind, but they happened to coincide with some of the trajectory changes. Correlation isn't causation, as every scientist knows, but when you're studying something unprecedented, even correlations become interesting. Were the radio emissions related to the acceleration? Were they both symptoms of the same underlying process? Or was it all just coincidence, our pattern-seeking brains finding connections where none existed? As 3I/Atlas continued its journey out of our solar system, these questions remained unanswered. The object grew fainter, the observations became harder, and eventually, even our best telescopes could no longer track it. But the data remained, waiting to be reanalyzed, reinterpreted, perhaps understood in new ways as our knowledge grew. The trajectory of 3I/Atlas, with all its subtle anomalies and unexplained variations, became part of a growing dataset on interstellar objects. 3 visitors, three sets of mysteries. Were we seeing the natural variation in a phenomenon we didn't yet understand? Or were we glimpsing something more organized, more purposeful, more alien than we were ready to accept? Comparing the visitors, when you have only three examples of something, every comparison matters. Every similarity might be a fundamental characteristic. Every difference might be a crucial clue. With ʻOumuamua, 2I/Borisov, and 3I/ATLS, we had exactly 3 data points to understand an entirely new class of objects. It was like trying to understand all of biology by looking at a bird, a fish, and something that might be a platypus. Let's start with what they had in common. All 3 were interstellar, approaching our solar system on hyperbolic trajectories that meant they weren't bound to our sun. All 3 were discovered by automated survey telescopes, found almost by accident while looking for other things. All 3 were relatively small, tens to hundreds of meters across, not the massive objects some theories had predicted, and all 3 raised questions, though the nature of those questions varied dramatically. ʻOumuamua was the pioneer, the first confirmed interstellar object, and it seemed determined to be as weird as possible. Discovered in October 2017 by the Pan-STARRS telescope in Hawaii, it was already on its way out of the solar system when we spotted it. We had just weeks to study it before it became too faint to observe. Everything about ʻOumuamua was unusual. Its shape, inferred from how its brightness varied as it tumbled through space, was unlike anything in our solar system. Either a 400-meter-long cigar or a 100-meter-wide pancake, depending on which models you believed. Its color was reddish, suggesting either organic compounds or cosmic ray processing over vast timescales. It showed no coma or outgassing despite passing close to the sun, and most mysteriously, it accelerated as it left our solar system in a way that couldn't be explained by gravity alone. The acceleration was the real puzzle. Comets accelerate due to outgassing, but ʻOumuamua showed no signs of outgassing. Various explanations were proposed. Maybe it was outgassing hydrogen, which would be invisible to our instruments. Maybe it was so porous that tiny amounts of outgassing could produce significant acceleration. Maybe, as Avi Loeb suggested, it was actually a light sail pushed by solar radiation pressure. The light sail hypothesis was bold, but not entirely unreasonable. For radiation pressure to produce the observed acceleration, ʻOumuamua would need to be extremely thin, perhaps less than a millimeter thick. This seemed unlikely for a natural object, but not impossible. Nature can produce surprising structures, but it would be exactly what you'd expect for an artificial light sail. Then came 2I/Borisov, discovered in August 2019 by amateur astronomer Gennady Borisov. This retry key continued it. Object was everything, ʻOumuamua wasn't. Clearly a comet, with a bright coma and a streaming tail. Its spectrum showed typical cometary molecules, cyanogen, diatomic carbon, water vapor. Its behavior was predictable. Its acceleration explained perfectly by observed outgassing. If anything, Borisov was remarkable for being unremarkable. It looked and acted exactly like comets from our own solar system, just happening to be from somewhere else. This normalcy was actually profound. It suggested that the processes that form comets might be universal, that the same physics and chemistry operate around other stars. Borisov was like finding out that trees on an alien planet still had leaves and bark. Familiar, reassuring, a confirmation that the universe follows consistent rules. But Borisov had its own subtle mysteries. Its composition, while generally comet-like, showed some interesting variations. It had an unusually high concentration of carbon monoxide relative to water, suggesting it formed in a very cold environment, perhaps the outer regions of its home system. Its dust was unusually fine-grained, and its nucleus was small, maybe only a few hundred meters across. Some astronomers noted that Borisov's trajectory brought it unusually close to the Sun for an interstellar object. Not impossibly close, but statistically unlikely if interstellar objects were randomly distributed. Was this just chance, or was there something about our solar system that attracted or selected for certain trajectories? And then there was 3I/ATLS, discovered in December 2019, the third member of our strange trio. It seemed to fall somewhere between its predecessors. Like Borisov, it showed a coma, clear evidence of outgassing, but like ʻOumuamua, its behavior didn't quite match expectations. The acceleration anomalies were more subtle than ʻOumuamua's, but more complex than Borisov's. The outgassing was visible but insufficient to explain the trajectory changes. The composition was comet-like, but with unusual ratios and unexpected compounds. It was as if someone had taken a normal comet and modified it slightly, just enough to make it interesting. When you laid out the properties of all three objects, patterns began to emerge, or perhaps patterns that we wanted to see emerged. All three were small, much smaller than many predicted interstellar objects should be. This might be selection bias. We can only detect objects that come close and are bright enough, but it might also tell us something about what gets ejected from star systems. The trajectories were interesting too. None of the three objects came from or were heading toward any obvious stellar source. Their paths seemed random, as you'd expect for objects that had been drifting for millions of years. But the fact that we'd detected three in such quick succession, after missing them throughout human history, raised questions about their true distribution. Some researchers propose that interstellar objects might come in waves or clusters. Perhaps certain events, stellar collisions, supernovae, planetary system disruptions, send bursts of objects into interstellar space. If we happen to be passing through such a cluster now, it would explain the sudden detections. Others suggested that the objects might not be randomly distributed at all. If they were artificial probes, they might be concentrated along certain routes or focused on systems of interest. Our solar system, with its obvious biosignatures and technological emissions, might be particularly interesting to study. The composition comparisons were revealing too. Borisov's fairly normal cometary composition suggested that at least some interstellar objects were exactly what we expected. Regular comets ejected from regular star systems, but ʻOumuamua and 3I/ATAAs, with their unusual properties, suggested that either there was much more variation in interstellar objects than expected, or that not all of them were natural. One researcher compiled a statistical analysis of the three objects, looking for correlations that might not be obvious from individual study. They found some intriguing patterns. All three objects had perihelia closest approach to the Sun within a relatively narrow range, closer than would be expected from random trajectories. All three were discovered when our detection capabilities had recently improved, suggesting many more might have passed undetected. And all three showed at least some anomalous behavior, even Borisov with its unusual CO content and grain size. The timing was particularly interesting. 3 objects in 3 years, then nothing for several years after. Was this just the luck of discovery, or was there something special about that period? Solar activity, Earth's position in its orbit, the alignment of our survey telescopes, many factors could have contributed, or perhaps there really was a cluster of objects passing through during those years. Some scientists began developing what they called the filtered probe hypothesis. The idea was that if alien civilizations were sending probes through the galaxy, they wouldn't all be the same. Some might be designed to look completely natural, like Borisov, to avoid detection. Others might have more obvious artificial characteristics, like ʻOumuamua's strange shape and acceleration. Still others might be somewhere in between, like 3I/ATLAs. This diversity would serve multiple purposes. Natural-looking probes could study systems without alerting potentially hostile civilizations. More obvious probes might be intended to make contact with civilizations that had reached a certain technological level. The variety would also provide redundancy. If one type of probe failed or was destroyed, others might succeed. It was a compelling idea, but completely unprovable, with just 3 objects. We'd need dozens, hundreds, maybe thousands of interstellar visitors to build up enough statistics to test such hypotheses. And at the current detection rate, that would take centuries. But there were other ways to approach the problem. Some researchers began looking through historical astronomical records for objects that might have been interstellar visitors, misidentified as comets. Others developed new search algorithms, optimized for finding hyperbolic orbits in telescope data. Still others proposed dedicated missions to intercept future interstellar objects, to study them up close or even return samples. The European Space Agency's Comet Interceptor mission, planned for launch in the late 2020s, was designed with exactly this possibility in mind. Parked at a gravitational balance point, it would wait for an interesting target, either a fresh comet from our outer solar system or an interstellar visitor, then race to intercept it. Similar missions were proposed by NASA, the Chinese Space Agency, and private organizations. The idea of actually visiting an interstellar object, of touching something from another star system, was too tantalizing to ignore. Even if they were completely natural, They would tell us about conditions in other systems, about the materials and processes that operate around alien suns. But what if they weren't natural? What if a close encounter revealed clear signs of technology, hull plating, antenna arrays, propulsion systems, or something completely unrecognizable but undeniably artificial? The scientific, philosophical, and cultural implications would be staggering. As we compared our 3 known interstellar visitors, these possibilities hung in the air, unspoken in formal papers, but discussed in hallways and coffee rooms. ʻOumuamua, the weird pioneer; Borisov, the reassuringly normal. 3I/ATLAS, the enigmatic middle ground. 3 objects, 3 mysteries, 3 pieces of a puzzle we were only beginning to understand. Were they telling us that the galaxy was full of ordinary debris, occasionally weird but ultimately natural? Or were they the first hints of something more organized, more intentional, more alien than we were prepared to accept? With only 3 data points, we couldn't tell, but each one added to our understanding, building a picture that was still blurry but gradually, tantalizingly, coming into focus. The chemical signatures. Chemistry doesn't lie. It might be hard to interpret, it might be obscured by noise or contamination, but the fundamental signatures of elements and molecules are universal. When light passes through or reflects off matter, it carries with it a fingerprint of what it encountered. This is how we know what distant stars are made of, what exists in the atmospheres of exoplanets, what comets carry in their ice, and it's how we tried to understand what 3I/ATLAS really was. Spectroscopy is the art of reading these chemical fingerprints. You take the light from an object, spread it out into its component colors, and look for dark lines where specific wavelengths have been absorbed, or bright lines where they've been emitted. Each element, each molecule, has its own unique pattern. It's like a barcode written in light. When astronomers first turned their spectrographs toward 3I/ATLAS, they expected to see familiar patterns. Comets, whether from our solar system or beyond, should be made of similar stuff: water ice, carbon dioxide, methane, ammonia, with traces of more complex organic molecules. The ratios might vary, the overall composition might differ slightly, but the basic vocabulary should be the same. And at first glance, that's what they saw. The spectrum showed clear signs of cyanogen, CN, and diatomic carbon, C-thys, 2 molecules commonly seen in comets. There were hints of water vapor, evidence of sublimating ice. Nothing immediately screamed alien or artificial, but as better data came in, as more sophisticated analyses were performed, subtleties emerged that made researchers pause. The ratios were off, not dramatically, but consistently. The amount of cyanogen relative to carbon was unusual. The water signatures were weaker than expected, given the amount of visible outgassing, and there were extra lines in the spectrum, absorption and emission features, that didn't match any of the usual cometary suspects. One team spent weeks trying to identify these mystery lines. They compared them against databases of thousands of molecules, looked for combinations that might produce similar patterns, even considered the possibility of measurement error or instrumental artifacts. But the lines persisted across multiple observations from different telescopes. They were real. The best match they could find was for a class of complex carbon chains, molecules that could form in space but were rarely seen in such abundance. These weren't impossible molecules, nothing that violated chemistry or physics, but they were unexpected. It was like finding a common bird with a few feathers of an impossible color, not entirely alien, but definitely not normal. Temperature played a role too. The spectral lines weren't just about what molecules were present, but what state they were in. Molecules at different temperatures emit and absorb light differently. The patterns from 3I/ATLAS suggested temperatures that didn't quite match what models predicted based on solar heating alone. Some regions seemed too warm, as if heated by some internal source. Others seemed too cold, as if insulated from solar radiation. The overall picture was of an object with a complex thermal structure, not the relatively simple ice ball warming in sunlight scenario of a typical comet. One particularly intriguing discovery involved isotope ratios. Isotopes are versions of elements with different numbers of neutrons. For example, carbon-12 and carbon-13 are both carbon, but with slightly different masses. The ratio of isotopes can tell you about where and how material formed. In our solar system, isotope ratios are remarkably consistent. varying only slightly based on distance from the Sun and processing history. But 3I/ATLAS showed isotope ratios that were distinctly different. Not impossible, but definitely foreign. It was chemical proof that this object had formed around a different star under different conditions, possibly billions of years ago. The deuterium to hydrogen ratio was particularly interesting. Deuterium is heavy hydrogen, with an extra neutron. In our solar system, the D/H ratio varies depending on where you look. It's different in Earth's oceans than in Jupiter's atmosphere, or in comets from the Oort cloud. But 3I/ATLAS's ratio didn't match any of these. It was either much higher or much lower, depending on which measurements you trusted. This could tell us about the conditions in 3I/ATLAS's home system. A high DLSH ratio might indicate formation in an extremely cold environment or around a star with unusual properties. A low ratio might suggest processing at high temperatures or interactions with stellar wind. But some researchers noted that the ratio was suspiciously close to what you might design if you wanted to optimize certain nuclear reactions. That was the thing about the chemical signatures. They were always just at the edge of being explicable naturally. Nothing that screamed artificial, but plenty that whispered unusual. It was like looking at a forest where all the trees were real species, but arranged in patterns that might be natural or might be a garden. The organic molecules were particularly fascinating. Comets often carry complex organics, the building blocks of life, but 3I/ATLAS's organics were different. They included the usual suspects: methanol, formaldehyde, hydrogen cyanide, but also more complex molecules that were hard to identify precisely. Some appeared to be long-chain hydrocarbons, others might have been amino acid precursors, and still others remained unidentified. One researcher, half joking but half serious, noted that the mixture looked almost optimized for panspermia, the idea that life could spread between star systems via comets or asteroids. The right molecules in the right proportions, protected by ice but able to be delivered to planetary surfaces. Was this coincidence, natural selection operating on cosmic scales, or something more intentional? The mineral content, inferred from infrared observations and dust analysis, added another layer of mystery. Most comets contain silicates, iron compounds, and various other minerals formed in the protoplanetary disk of their home system. 3I/ATLAS had these, but also showed signatures of more exotic materials. There were hints of what might be titanium compounds, unusual in cometary material, but not impossible. There were suggestions of rare Earth elements in proportions that didn't match solar system patterns, and there were spectral features that might indicate manufactured materials, ceramics, alloys, or composite materials, though the evidence was far from conclusive. The challenge with all these observations was distinguishing between unusual for our solar system and artificially produced. An object from a system with different initial conditions, a different stellar metallicity, or a different formation history could naturally have chemistry that seemed exotic to us. But as one researcher put it, at what point does exotics become engineered? If you found a rock with naturally occurring steel in it, you'd assume it was artificial because the probability of iron and carbon combining in just the right way naturally is essentially zero. But what if you didn't know what steel was? What if you came from a world where such combinations were common? This was the interpretive challenge with 3I/ATLAS's chemistry. We knew what natural looked like in our solar system. We could theorize about what natural might look like in other systems, but we had no reference point for what artificial would look like if someone was trying to make it look natural. Some researchers proposed that we might be looking at a kind of camouflage. If you wanted to send a probe through the galaxy without it being immediately recognized as artificial, you'd make it look like a comet. You'd cover it in ice and dust, include the right molecules in roughly the right proportions. But you might not get everything perfect. There might be telltale signs in the chemistry, subtle anomalies that would only be noticed by someone looking very carefully. Others suggested we might be seeing the results of billions of years of processing. Even if 3I/ATLAS started as a completely natural object, eons of cosmic ray exposure, thermal cycling, and chemical reactions could have altered its composition in unusual ways. The galaxy is a vast chemical laboratory, and we were only beginning to understand what experiments it might conduct. There was also the possibility of contamination or alteration during 3I/ATLAS's passage through our solar system. The solar wind, magnetic fields, Even gravitational stresses could potentially trigger chemical changes. Some of the anomalies might not be inherent to the object, but rather the result of its interaction with our local environment. As 3I/Atlas faded from view, its chemical secrets went with it. We were left with spectra, measurements, theories, but no samples, no chance for the detailed laboratory analysis that might resolve the ambiguities. The chemistry told a story, but it was written in a language we didn't fully understand, with words that could mean different things depending on context we didn't have. Was 3I/ATLS a natural comet with an unusual composition, a probe disguised as a comet, something else entirely? The chemistry alone couldn't tell us, but it added crucial data to our growing understanding of interstellar objects. Each spectrum, each anomaly, each unexplained line was a piece of a puzzle that we were only beginning to assemble. The brightness variations. Light is information. Every photon that reaches our telescopes carries data about its source, composition, temperature, motion, shape. When astronomers studied 3I/ATLS, they weren't just measuring how bright it was, but how that brightness changed over time. These variations, plotted as curves on graphs, told stories about the object's rotation, its shape, its surface properties, maybe even its purpose. A perfect sphere rotating in space maintains constant brightness as seen from Earth. But real objects aren't perfect spheres. They're elongated, irregular, bumpy. As they rotate, they present different faces to us and to the sun, creating predictable patterns in their brightness. These patterns, called light curves, are like fingerprints. No two objects have exactly the same one. 3I/Atlas's light curve was, to put it mildly, strange. First, there was the amplitude, the difference between its brightest and dimmest appearances. For most comets, this variation is modest, maybe a factor of 2 or 3. They're roughly spherical, maybe a bit elongated, but nothing extreme. 3I/ATLAS varied by a factor of 10, sometimes more. This suggested either an extremely elongated shape or dramatic changes in reflectivity across its surface. The period was puzzling too. Most small solar system bodies rotate with periods of hours to days. 3I/ATLAS seemed to have multiple periods superimposed. A primary rotation of about 18 hours, but with secondary variations on timescales of days and weeks. It was as if the object was not just spinning but tumbling in a complex non-principal axis rotation. This kind of rotation isn't unheard of. Objects that have been recently disturbed by collisions, close encounters, or outgassing torques can enter these complex rotational states, but they usually dampen quickly, settling into simpler rotation patterns. 3I/ATLAS showed no signs of dampening during our observations. If anything, its rotation seemed to be getting more complex over time. Then there were the glitches, sudden changes in brightness that didn't fit any rotational pattern. The object would be following its usual variation, then suddenly brighten or dim for a few hours before returning to the pattern. These events seemed random at first, but statistical analysis suggested they might be clustered, happening more often at certain rotational phases. Some astronomers proposed that these glitches were caused by outgassing jets turning on and off. As different regions of the surface were exposed to sunlight, pockets of volatile ice might suddenly sublimate, creating bright jets that enhanced the object's brightness. When the pocket was exhausted or rotated into shadow, the jet would stop. But the timing didn't quite work. The glitches didn't correlate well with 3I/ATLAS's orientation relative to the sun. Some happened when the same face had been in sunlight for hours, others when a region had just rotated into view. It was as if the object was deciding when to brighten, not just responding to solar heating. The spectral characteristics of these brightness changes added another layer of mystery. Usually, when a comet brightens due to outgassing, the color changes slightly as gas and dust contribute differently to the reflected light. But 3I/ATLAS's color remained remarkably constant during many of its brightness variations. The object was getting brighter or dimmer without changing what was causing the brightness. One explanation involved surface composition changes. Perhaps 3I/ATLAS had patches of different materials, bright ices, dark organics, metallic regions that reflected light differently. As it rotated, we'd see different combinations of these materials, but this didn't explain the glitches or the complex periodicity. Another theory proposed that 3I/ATLS might be fragmenting in a controlled way, not breaking apart randomly, but shedding pieces at specific times. Each fragmentation event would change the object's shape, and thus its light curve. If the fragmentation followed some kind of pattern or program, it might explain the seemingly purposeful timing of brightness changes. This led to one of the more speculative interpretations, that the brightness variations were intentional, a form of signaling. The idea wasn't as crazy as it might sound. If you wanted to announce your artificial nature to observers without using radio signals or other active measures, modulating your brightness in clearly non-natural patterns would be one way to do it. Some researchers spent considerable time analyzing 3I/ATLS's light curve for mathematical patterns. They looked for prime number sequences, Fibonacci patterns, mathematical constants like pi or e. They applied Fourier transforms, wavelet analyses, and various decoding algorithms. Most found nothing conclusive, but a few claimed to detect subtle patterns that might be significant. One team argued that the brightness variations encoded a binary message when properly sampled and thresholded. Another suggested that the complex rotation was actually a three-dimensional projection of a four-dimensional rotation, though what that might mean physically was unclear. These claims were met with appropriate skepticism, but they couldn't be entirely dismissed. The comparison with ʻOumuamua's light curve was inevitable and revealing. That first interstellar visitor had shown dramatic brightness variations too, suggesting its extremely elongated or flattened shape. But ʻOumuamua's variations had been relatively regular, consistent with a simple rotation. 3I/ATLAS was showing something far more complex. If both objects were natural, it suggested that interstellar objects could have a wide variety of shapes and rotational states, perhaps preserved from violent ejection events in their home systems. But if either or both were artificial, the light curves might be telling us something about their function or design. Consider the engineering perspective. If you were designing a probe to travel between stars, what shape would you choose? A sphere minimizes surface area for a given volume, good for protection against cosmic rays. A needle shape minimizes cross-section in the direction of travel, reducing drag from interstellar medium. A flat sheet maximizes surface area for solar panels or light sails. 3I/ATLS's light curve suggested it might be all of these at once, or none of them. Its shape seemed to change, not just appear different from different angles, but actually reconfigure. This could be explained by fragmentation or complex rotation, but it could also be explained by an object that was deliberately changing its shape. Advanced materials could make such shape changing possible. Smart materials that respond to temperature, radiation, or magnetic fields. Swarms of smaller objects, maintaining formation, but adjusting their relative positions. Or something more exotic, technologies we haven't imagined yet. The brightness variations also provided clues about 3I/ATLS's surface properties. The way light scattered from the object suggested a complex surface texture, not smooth like a polished sphere, not uniformly rough like a typical asteroid, but something in between with regions of different textures that seemed to change over time. Some of these changes could be explained by sublimation altering the surface, ice turning to gas and leaving behind different material. But the rate and pattern of changes didn't match models of cometary evolution. It was as if the surface was being actively modified, not just passively eroding. Near-infrared observations added another puzzle. In these wavelengths, 3I/ATLS showed thermal emission from its surface, but the thermal patterns didn't match the optical brightness variations. Sometimes the object was optically bright, but thermally dim, other times the reverse. This suggested that different mechanisms were controlling visible light reflection and heat emission. One possibility was that 3I/ATLS had a kind of thermal regulation system. Areas that got too hot would change their properties to emit more heat or reflect more sunlight. Areas that cooled would become more absorbing. This kind of behavior could emerge naturally from certain material compositions, but the observed patterns seemed too organized, too efficient. As 3I/ATLS moved farther from the sun, its brightness variations should have become simpler. Less heating meant less outgassing, which should have meant more regular rotation and fewer glitches. Instead, the variations became more complex. New periodicities appeared, the glitches became more frequent, though smaller in amplitude. It was as if the object was responding to decreasing solar input by increasing some internal activity, like a probe switching from solar power to internal power, changing its behavior to match new conditions, or like a natural object with complex internal structure, finally revealing dynamics that had been masked by solar-driven activity. The final observations of 3I/ATLS, just before it became too faint to detect, showed something remarkable. The brightness variations suddenly simplified, settling into a regular pattern with a single period of about 8.7 hours. Then, in the very last reliable measurement, the object flared, brightening by a factor of 50 for just a few minutes before fading below detectability. Was this a final outgassing event as some last pocket of volatile ice was exposed? A collision with a small meteoroid? The deployment of a reflective surface? Or perhaps a farewell signal? A last bright flash before heading back into the darkness between stars? We'll never know. Hole 3I/ATAAS is gone now, too far and too faint for even our best telescopes. But its light curve remains, recorded in databases, plotted in papers, analyzed and reanalyzed by researchers looking for patterns, meanings, messages. Every variation, every glitch, every anomaly is preserved, waiting for new insights or new contexts that might explain what we saw. The brightness variations of 3I/ATLS told us that this was not a simple object following simple rules. Whether natural or artificial, it was complex, dynamic, and surprising. It challenged our understanding of how objects should behave and forced us to consider possibilities we might otherwise have dismissed. The question of technology. At what point does unusual become artificial? When do enough anomalies accumulate that we have to seriously consider the possibility that we're not looking at a natural phenomenon? With 3I/ATS, as with ʻOumuamua before it, these questions moved from philosophical musing to practical scientific consideration. The conservative approach in science is to exhaust natural explanations before considering artificial ones. It's a good principle, protecting us from wishful thinking and sensationalism, but it can also blind us to genuine discoveries if we're too rigid in its application. The history of science is littered with phenomena initially dismissed as impossible that turned out to be real. So let's consider carefully and seriously what it would mean if 3I/ATLS or its interstellar siblings were technological rather than natural objects. First, we need to establish what we mean by technology in this context. We're not necessarily talking about gleaming metal spacecraft with obvious engines and antennas. Technology, especially technology designed to survive interstellar journeys lasting millions of years, might look very different from our expectations. Consider the requirements for an interstellar probe. It needs to survive radiation, micrometeorite impacts, and extreme temperature variations for geological timescales. It needs to operate without maintenance, possibly without any active control for most of its journey. It needs to be light enough to be accelerated to interstellar velocities, but robust enough to survive the journey. One solution might be to make it look natural, cover it in rock and ice that would accumulate anyway, use materials that mimic asteroids or comets, hide the technological components deep inside, protected by natural-looking shells. This isn't deception necessarily, just good engineering. Why fight the space environment when you can blend with it? This camouflage hypothesis could explain many of 3I/ATLS's anomalies: the unusual composition, artificial materials mixed with natural ones, the strange brightness variations, active surfaces or deployed instruments, the trajectory anomalies, propulsion or navigation systems, making small adjustments. But how would such technology work? Our rockets and ion drives are obvious, producing clear signatures, but there might be more subtle approaches. Consider a few possibilities. Magnetic sailing could use the galactic magnetic field for propulsion. By generating their own magnetic fields, objects could push against the galaxy's field, creating thrust without expelled material. The acceleration would be tiny, but could add up over millions of years, and it might be nearly undetectable from Earth. Solar or stellar radiation pressure could be harvested more efficiently than we currently imagine, not with obvious sails, but with materials that change their reflectivity or absorptivity in response to conditions. The object could literally surf on starlight, adjusting its properties to maintain or change course. Exotic propulsion methods we haven't discovered yet could be at play, perhaps manipulation of zero-point energy, interaction with dark matter, or technologies that would seem like magic to us. Arthur C. Clarke's famous law that sufficiently advanced technology is indistinguishable from magic might apply here. But propulsion is just one aspect. What about the probe's mission? What would it be designed to do? One possibility is passive observation. The probe might simply be recording data as it passes through systems, building a map of the galaxy's stars, planets, and potentially life-bearing worlds. It wouldn't need to transmit constantly, perhaps only when it encounters something interesting or reaches certain milestones. Another is active sampling. The probe might be collecting material, analyzing chemical compositions, even gathering biological samples if it encounters them. The apparent fragmentation of 3I/ATAS could have been sample collection devices being deployed. Communication is another consideration. If 3I/ATLAS was artificial, was it trying to communicate? The brightness variations. Some researchers interpreted as signals could have been attempts at contact, or perhaps communication was happening in ways we weren't equipped to detect. Neutrino beams, gravitational waves, quantum entanglement, or methods we haven't conceived of. The timing of these interstellar visitors raises its own questions. Why 3 in 3 years after none in recorded history? If they're natural, it might be coincidence or a clustering effect, but if they're artificial, it might be intentional. Perhaps Earth recently passed some threshold that made it interesting to observe. Our radio emissions have been spreading into space for about a century. Our nuclear tests, industrial pollution, and climate changes have altered our planet's signatures. Maybe we triggered some kind of automated interest from probes that had been waiting and watching. Or perhaps this is routine surveillance that we're only now able to detect. If the galaxy is full of probes, constantly monitoring and reporting, we might be seeing the normal traffic finally visible thanks to our improved telescopes. The variety among the three objects, ʻOumuamaua's bizarre shape and acceleration, Borisov's apparent normalcy, 3I/ATLAS's complex behavior, could represent different designs for different purposes. Reconnaissance probes, communication relays, sample collectors, or purposes we can't fathom. There's also the unsettling possibility that these objects aren't probes in the traditional sense, but something more autonomous, not just programmed machines but artificial intelligences, capable of making decisions, adapting to situations, perhaps even having goals and desires of their own. This might sound like science fiction, but consider the practicality. Any civilization sending probes across interstellar distances would face communication delays of years to millennia. The probes would need to be autonomous, capable of handling unexpected situations without guidance. Over time, that autonomy might evolve into something resembling consciousness. If 3I/Atlas was not just artificial but intelligent, its behavior takes on new dimensions. The brightness variations might not be signals, but thoughts. The trajectory changes might not be navigation, but decisions. The fragmentation might not be mechanical failure, but intentional division, perhaps even reproduction. But let's step back from speculation and return to evidence. What would convince the scientific community that an interstellar object was artificial? Clear geometric structures would be compelling. Right angles, perfect spheres, repeated patterns that nature doesn't produce. But these might be hidden beneath accumulated material, or deliberately obscured. Exotic materials in unnatural combinations or proportions would be significant, but distinguishing unnatural for our solar system from artificially produced is challenging without samples. Behaviors that clearly violate known physics or require intelligent control would be decisive, but our understanding of physics is incomplete, and natural processes can mimic intelligence in surprising ways. Radio or other electromagnetic signals encoding information would be the smoking gun. But if such signals exist, they might be in formats we don't recognize or at frequencies we weren't monitoring. The challenge is that any sufficiently advanced technology might be indistinguishable not from magic but from nature. If you can build at the molecular level, your artifacts might look organic. If you can manipulate fundamental forces, your propulsion might seem like anomalous acceleration. If your technology is millions of years old, it might be so degraded or camouflaged that its artificial origin is completely hidden. This is why the question of technology in interstellar objects remains open. We don't have proof that any of them are artificial, but we also don't have proof that they're natural. We have anomalies, patterns, suggestions, but no certainty either way. As our detection capabilities improve, we'll spot more interstellar visitors. Each one will add data to our understanding. Eventually, patterns might emerge that clearly indicate natural or artificial origin. Or we might discover that the distinction isn't as clear as we thought, that there are categories of objects we haven't imagined. Until then, we're left with tantalizing mysteries. Objects from other stars, behaving in ways we don't fully understand, challenging our assumptions about what moves between the stars. Whether they're natural wonders or technological artifacts, they're expanding our perspective on our place in the cosmos. Historical perspectives. The idea that objects from beyond our solar system might visit us isn't new. Long before we had the telescopes to detect them, or the mathematics to calculate their orbits, humans wondered about visitors from the stars. These early thoughts, mixing mythology, philosophy, and proto-science, laid the groundwork for how we think about interstellar objects today. Ancient cultures had various beliefs about meteors, comets, and other celestial phenomena. Many saw them as messages from gods, omens of change, or souls traveling between worlds. The Greeks called them aster, meaning star, and meteor, meaning high in the air. They didn't know these objects came from space, but they recognized them as something beyond ordinary earthly experience. In China, astronomers kept meticulous records of guest stars and broom stars, novae and comets that appeared unexpectedly in the heavens. The Han Dynasty, astronomers in particular, noted objects that didn't follow the regular patterns of planets and stars. Some of their descriptions, viewed through modern eyes, might have been observations of interstellar visitors, though we'll never know for certain. The medieval Arabic astronomers made similar observations, often with greater precision than their European contemporaries. They distinguished between different types of transient celestial phenomena and speculated about their origins. Some proposed that comets came from beyond the sphere of the moon, a radical idea that wouldn't be widely accepted in Europe for centuries. The scientific revolution brought new tools and new ideas. When Galileo turned his telescope skyward in 1609, he revealed that the cosmos was far more complex than previously imagined. Comets, in particular, became objects of intense study. The debate over whether they were atmospheric phenomena or celestial bodies raged for decades. Edmund Halley's successful prediction of a comet's return in 1758 proved that at least some comets orbited the Sun, but it also raised questions. If comets could have such elongated orbits, taking them far beyond the known planets, might some come from even farther? Could there be comets that visited once and never returned? By the 19th century, astronomers had developed the mathematical tools to calculate orbits precisely. They discovered that some comets had nearly parabolic orbits, meaning they were barely bound to the Sun. A small change in velocity, a gravitational perturbation from a planet, could send them on hyperbolic trajectories, never to return. This led to speculation about truly hyperbolic comets, objects that entered our solar system from interstellar space. Several candidates were proposed over the years, but better observations always revealed them to be long-period comets from our own system's outer reaches. The first serious scientific consideration of interstellar objects came in the early 20th century. Ernst Öpik, in 1932, calculated that objects ejected from other star systems should occasionally pass through ours. He estimated their frequency and velocity distribution, work that proved remarkably prescient when compared to modern observations. In 1950, Jan Oort proposed his famous cloud, a vast sphere of icy bodies surrounding our solar system. This provided a source for long-period comets, but it also suggested a mechanism for creating interstellar objects. Gravitational perturbations could eject objects from the Oort cloud entirely, sending them into interstellar space. If our system did this, so must others. Fred Whipple, who developed the dirty snowball model of comets, speculated about interstellar comets in the 1960s. He suggested they might be detectable by their hyperbolic orbits and potentially unusual compositions. He even proposed that some might be artificial, perhaps probes from other civilizations, though this idea was generally considered too speculative for serious consideration. The 1970s brought a surge of interest in interstellar visitors, partly inspired by the space age and partly by growing interest in the search for extraterrestrial intelligence SETI. Scientists like Carl Sagan popularized the idea that advanced civilizations might send probes to other star systems. the concept of Bracewell probes, autonomous spacecraft that could explore and report back over millions of years, entered scientific discourse. During this period, several astronomers claimed to have detected hyperbolic comets. Comet Kotek in 1973 was initially thought to be interstellar, generating enormous public interest, but refined calculations showed it was merely a long-period comet from our own system. Similar false alarms occurred with other comets, each teaching astronomers more about the challenges of identifying true interstellar objects. The 1980s and 1990s saw improvements in detection technology and orbital calculation methods. Charge-coupled devices, CCDs, replaced photographic plates, allowing much fainter objects to be detected. Computer automation enabled surveys of larger areas of sky. Scientists knew it was only a matter of time before a genuine interstellar object was found. Science fiction, meanwhile, explored the possibilities. Arthur C. Clarke's Rendezvous with Rama, 1973, depicted a cylindrical interstellar object passing through our solar system, later revealed to be an alien spacecraft. The novel's influence on how both scientists and the public thought about interstellar visitors cannot be overstated. When Cosmo's elongated shape was revealed, Rama was immediately invoked in discussions. Gregory Benford and other science fiction authors explored more subtle scenarios. What if interstellar visitors weren't obvious spacecraft, but disguised as natural objects? What if they'd been passing through for millennia, unnoticed? These ideas, while fictional, influenced how scientists thought about detection strategies and potential signatures. By the early 2000s, several research groups were actively searching for interstellar objects. They knew the theoretical prediction: there should be about one asteroid-sized interstellar object within the orbit of Neptune at any given time, but finding it required looking at the right place at the right time with sufficient sensitivity. Projects like Pan-STARRS, Panoramic Survey Telescope and Rapid Response System were designed primarily to find potentially hazardous asteroids, but they were also ideal for detecting interstellar visitors. The wide-field surveys, repeated observations, and automated detection algorithms created a net that could catch these rare objects. When ʻOumuamua was discovered in October 2017, it vindicated decades of theoretical work. Here, finally, was proof that objects from other star systems could and did visit ours. The name Hawaiian for scout or messenger from afar seemed particularly appropriate, given the long history of wondering about such visitors. The reaction from the scientific community was electric. Papers flooded journals proposing explanations for ʻOumuamua's unusual properties and predicting characteristics of future discoveries. Some researchers dusted off old ideas about artificial probes now that there was an actual object to consider. Avir Loeb's suggestion that ʻOumuamua might be artificial sparked controversy, but also serious discussion. His book Extraterrestrial argued that scientists should be more open to considering artificial explanations for anomalous objects. While many disagreed with his conclusions, the debate highlighted how interstellar objects challenged our assumptions. The discovery of 2I/Borisov in 2019 provided a counterpoint. Here was an interstellar object that behaved exactly as predicted, a fairly normal comet that happened to be from another star system. It suggested that ʻOumuamua might be an outlier, not representative of typical interstellar visitors. But then came 3I/ETLE, adding new complexity to the picture. Neither as bizarre as a ʻOumuamua, nor as mundane as Borisov, it suggested a spectrum of interstellar objects with varying properties and possibly origins. Looking at this history, we see a progression from mythology to science, from speculation to observation. Each era's understanding of interstellar visitors reflected its technological capabilities and cultural preoccupations. Ancient cultures saw divine messages. The scientific revolution saw mechanical clockwork. The space age saw alien probes. What's remarkable is how certain themes persist across cultures and centuries. The idea of messages or messengers from beyond. The notion that these objects might be artificial or purposeful. The sense that they're telling us something important about our place in the cosmos. Modern indigenous knowledge holders have noted parallels between scientific discoveries and traditional stories. Some Pacific Island cultures have legends of voyaging stars, objects that travel between worlds carrying knowledge or life. Aboriginal Australian traditions speak of objects falling from the sky that connect Earth to other realms. While we must be careful not to over-interpret these stories, They remind us that humans have always wondered about visitors from beyond. The historical perspective also reveals how our assumptions shape our observations. When we expected interstellar objects to be icy comets, we built models around that expectation. When ʻOumuamua defied those models, we had to scramble for explanations. Each discovery forces us to revise our assumptions, expanding our conception of what's possible. This history isn't just academic. It influences how we interpret new data, what questions we ask, what possibilities we consider. The researchers studying 3I/ATLAS were informed by centuries of thought about interstellar visitors, from ancient mythology to modern astrophysics. As we detect more interstellar objects, and we will as our surveys improve, this history will continue to evolve. Each new visitor will be interpreted through the lens of what came before, but also has the potential to revolutionize our understanding. Perhaps future historians will look back at the early 21st century as the moment when humanity first confirmed that objects from other stars visit our solar system. They might see ʻOumuamua, Borisov, and 3I/ATLAS as the beginning of a new era of discovery. Or they might see them as early hints of something even more profound, evidence that we're not alone in the cosmos, that intelligence and technology exist beyond Earth. The history of thinking about interstellar visitors reminds us that big ideas often take time to be accepted. Continental drift was considered absurd until it became plate tectonics. The notion that rocks could fall from space was dismissed until meteorites were accepted. The idea that objects from other star systems could visit ours was speculation until it was fact. What ideas about interstellar visitors do we currently dismiss that might one day be accepted? What assumptions do we hold that future discoveries will overturn? History suggests we should keep an open mind while maintaining scientific rigor, ready to be surprised by what the cosmos reveals. Scientific debates. Science thrives on disagreement, not hostile argument, but vigorous debate over evidence, interpretation, and implications. The discovery of interstellar objects, particularly the anomalous behavior of ʻOumuamua and 3I/ATLAS, has sparked some of the most intense scientific debates of recent years. These discussions, happening in journals, conferences, and increasingly in public forums, reveal not just disagreements about specific objects, but fundamental questions about how we do science. The central debate, of course, is whether any observed interstellar objects might be artificial. This isn't a simple binary question, natural or artificial, but a complex spectrum of possibilities, each with its own advocates and critics. On one side are researchers like Avi Loeb, who argue that we should seriously consider artificial explanations for anomalous objects. Loeb's argument isn't that ʻOumuamua or 3I/ATLAS are definitely artificial, but that dismissing the possibility without thorough investigation is unscientific. He points to the accumulation of anomalies, unusual shapes, unexplained accelerations, strange compositions that strain natural explanations. Loeb and his supporters argue that the scientific community suffers from a bias against considering artificial explanations. This bias, they claim, stems from fear of being associated with pseudoscience, career concerns about studying controversial topics, and an overcorrection against the sensationalism that often surrounds claims of alien contact. They point out that we readily accept exotic natural explanations, hydrogen icebergs, dust bunnies in space, nitrogen ice fragments, that have never been observed before, while dismissing artificial explanations that might be simpler. If we saw a perfect sphere in space, they argue, would we strain to find a natural explanation, or would we accept that it might be manufactured? On the other side are researchers who maintain that extraordinary claims require extraordinary evidence, and that the evidence for artificial origin doesn't meet this standard. They argue that while the observed objects are certainly unusual, unusual doesn't mean artificial. The universe is full of strange phenomena that turned out to be natural once we understood them better. These scientists point out that every anomaly associated with interstellar objects has potential natural explanations, even if those explanations aren't perfect. ʻOumuamua's acceleration could be due to outgassing we couldn't detect. Its shape, while extreme, might result from collisional processes we haven't observed before. 3I/ATLAS's composition might reflect formation in a very different stellar environment. They also raise practical objections to the artificial hypothesis. If these objects are probes, why haven't we detected any signals from them? Why would alien civilizations send probes that look almost but not quite natural? How could technology survive millions of years in interstellar space? Between these positions is a middle ground occupied by many researchers who remain agnostic. They acknowledge the anomalies, recognize that natural explanations aren't fully satisfactory, but don't see enough evidence to invoke artificial origins. These scientists often focus on gathering more data, improving detection methods, and refining models rather than debating origin scenarios. The debate extends beyond individual objects to broader questions about how we should approach anomalous observations. Should we follow the traditional hierarchy of explanations, mundane natural, exotic natural, then artificial, or should we consider all possibilities simultaneously, weighing them based on evidence rather than predetermined preferences? There's also debate about the role of speculation in science. Some argue that speculating about artificial origins is unproductive, distracting from serious research, and potentially damaging to science's credibility. Others contend that speculation is essential for generating hypotheses and pushing the boundaries of knowledge. The public nature of these debates has added another dimension. Unlike many scientific discussions that happen within academia, the interstellar object debate has played out in popular books, news media, and social networks. This has brought public attention and funding to the field, but also introduced pressures and distortions that some scientists find uncomfortable. Funding agencies have had to grapple with whether to support research into potentially artificial interstellar objects. Is it responsible to spend public money investigating what might be alien probes? Or is it irresponsible not to investigate objects that could represent one of the most important discoveries in human history? The debate has also revealed disagreements about methodology. How do we study objects we can only observe briefly and from great distances? How do we distinguish between competing hypotheses when we can't perform controlled experiments? How much weight should we give to theoretical models versus observational data? Statistical arguments have become central to the debate. Some researchers argue that finding 3 unusual interstellar objects in quick succession is statistically unlikely if they're natural. Others counter that with a sample size of 3, we can't make meaningful statistical claims. The debate over statistics reflects deeper disagreements about how to reason with limited data. There are also philosophical dimensions to the debate. What is the null hypothesis, that interstellar objects are natural, or that we don't know? How do we balance skepticism with openness to new ideas? What is the cost of a false positive, claiming something is artificial when it's not, versus a false negative, missing genuine evidence of alien technology? The debate has sometimes become personal, with researchers questioning each other's motivations and competence. Some have accused advocates of the artificial hypothesis of seeking attention or selling books. Others have accused skeptics of being closed-minded or afraid to challenge orthodoxy. While such attacks are unfortunate, they reflect the high stakes and deep passions involved. International perspectives have added richness to the debate, where researchers from different countries and cultures bring different assumptions and approaches. Some cultures may be more open to considering non-natural explanations, while others might be more skeptical. This diversity of thought has been largely positive, preventing the debate from becoming too insular. The role of simulation and modeling has been contentious. Some researchers have created elaborate simulations showing how natural processes could produce objects like ʻOumuamua or 3I/ATLS. Others have modeled how artificial probes might behave and what signatures they'd leave. The debate over whose models are more realistic or relevant continues. Machine learning and artificial intelligence have entered the debate as tools for analyzing data and identifying patterns. Some researchers use AI to search for signals or anomalies that human analysts might miss. Others worry that AI might find patterns that aren't really there, or miss important features that don't fit its training. The debate has also touched on broader issues in science. How do we handle observations that don't fit our theories? When do we modify theories versus dismissing observations? How do we balance conservatism with revolutionary thinking? These questions go beyond interstellar objects to the heart of scientific progress. Looking forward, the debate is likely to intensify as we detect more interstellar objects. Each new discovery will provide data that supports or challenges existing hypotheses. Eventually, we might find an object so clearly natural or artificial that the debate is settled. Or we might discover that the natural-artificial distinction isn't as clear as we thought. The scientific debates around 3I/ATLAS and its companions are more than academic exercises. They're shaping how we search for and study interstellar objects, influencing funding decisions and affecting public perception of science. Most importantly, they're pushing us to confront fundamental questions about intelligence, technology, and our place in the universe. Whether these objects are natural or artificial, the debates they've sparked have value. They've forced us to examine our assumptions, improve our methods, and consider possibilities we might otherwise have ignored. In science, as in exploration, sometimes the journey is as important as the destination. Detection methods and limitations. Finding an interstellar object is like catching a snowflake in a blizzard while wearing a blindfold. These objects are small, fast, faint, and we usually don't know where to look until they're already leaving. The fact that we've detected any at all is a testament to human ingenuity and technological advancement. But our methods have limitations, and understanding these constraints is crucial for interpreting what we've found and what we've missed. The primary tool for detecting interstellar objects is the Wide Field Survey telescope. These instruments scan large portions of the sky repeatedly, looking for anything that moves against the background stars. Pan-STARRS in Hawaii, which found ʻOumuamua, can survey the entire visible sky every few nights. ATLAS, which discovered 3I/ATLAS, operates similarly but with different sensitivity and coverage. These surveys work by taking multiple images of the same region of sky and comparing them. Sophisticated software analyzes the images, identifying objects that have moved between exposures. The software must distinguish real objects from cosmic rays, satellite trails, aircraft, and various artifacts. It's a needle in a haystack problem, except the haystack is the entire sky and the needle is moving. The Catalina Sky Survey, primarily designed to find near-Earth asteroids, has also contributed to interstellar object detection. Located in Arizona, it uses multiple telescopes to survey the sky, particularly regions where asteroids are likely to appear. While optimized for solar system objects, it's capable of detecting interstellar visitors that venture close enough. The Large Synoptic Survey Telescope, now called the Vera Rubin Observatory, represents the next generation of survey capability. When fully operational, it will photograph the entire visible sky every few nights with unprecedented sensitivity. Researchers estimate it could detect dozens of interstellar objects per year, transforming our understanding of these visitors. But optical surveys have fundamental limitations. They can only detect objects that reflect enough sunlight to be visible. This means objects must be relatively large, tens of meters at least, relatively close, within a few astronomical units, and relatively reflective. A dark, small, or distant interstellar object could pass through our solar system unnoticed. The detection efficiency drops rapidly with distance from the Sun. An object at Jupiter's distance appears 25 times fainter than the same object at Earth's distance, all else being equal. This creates a strong selection bias toward objects that pass close to the inner solar system. We're missing the vast majority of interstellar objects that pass through the outer regions. There's also a timing issue. Interstellar objects move fast, typically 20–30 kilometers per second relative to the Sun. They spend only months to years in the observable zone. If we don't happen to be looking in the right direction at the right time, we miss them entirely. This temporal sampling bias means we're seeing only a tiny fraction of the true population. Once an object is detected, determining its orbit is the next challenge. This requires multiple observations over time to constrain the object's position and velocity. But interstellar objects don't give us much time. By the time we recognize something as interstellar, it's often already heading out of the system. Orbital determination for fast-moving objects is particularly challenging. Small errors in position measurements translate to large uncertainties in orbital parameters. This is why initial orbits are often revised as more observations come in. For 3I/ATLAS, the orbit was updated several times as astronomers gathered more data. Spectroscopy, analyzing the light from an object to determine its composition, faces its own challenges. Interstellar objects are faint, making it difficult to gather enough light for detailed spectral analysis. The spectra we do obtain are often noisy, with large uncertainties. Subtle compositional differences that might indicate artificial origin could be lost in the noise. The rapid motion of interstellar objects also complicates spectroscopy. the object's position changes significantly during long exposures, smearing the light and reducing spectral resolution. Adaptive optics and tracking systems help, but they're not perfect. Infrared observations, crucial for understanding an object's thermal properties and composition, are even more challenging. Infrared detectors are less sensitive than optical ones, and the sky is brighter in infrared. The Spitzer Space Telescope, before its retirement, provided valuable infrared data on ʻOumuamua, but such observations are difficult and rare. Radio observations have been attempted for all three known interstellar objects. The SETI Institute, Breakthrough Listen, and other groups have pointed radio telescopes at these visitors, searching for artificial signals. But radio observations face their own limitations. First, we don't know what frequencies to monitor. An alien transmission could be at any wavelength, using any modulation scheme. We can only sample a tiny fraction of the possible parameter space. Second, the objects are small and distant, meaning any transmissions would need to be powerful and directed toward Earth to be detectable. The rapid motion of interstellar objects also causes Doppler shifts that smear any potential signals across multiple frequencies. This makes narrowband signals, often considered the most likely form of artificial transmission, particularly hard to detect. Radar, which has been invaluable for studying near-Earth asteroids, is generally useless for interstellar objects. Radar requires enormous power to reach even nearby objects, and the return signal weakens with the fourth power of distance. By the time we detect interstellar objects, they're usually too far for radar investigation. Our detection methods also have geographical limitations. Telescopes in the northern hemisphere can't see the southern sky, and vice versa. Weather, daylight, and moonlight create gaps in coverage. An interstellar object could pass through unobserved simply because it was in the wrong part of the sky at the wrong time. There are also human limitations. Analyzing survey data, following up on potential detections, and coordinating observations all take time and resources. There are only so many astronomers, only so many telescopes, only so much funding. Choices must be made about what to observe and when. The COVID-19 pandemic illustrated these human factors. Several potential interstellar object discoveries in 2020 to 2021 received less follow-up than they might have otherwise, as observatories operated with reduced staff and travel restrictions prevented optimal observations. Data processing and storage present their own challenges. Modern surveys generate enormous amounts of data, petabytes per year. Storing, processing, and analyzing this data requires substantial computational resources. Potential interstellar objects might be hiding in archived data, waiting for better algorithms or more thorough analysis to reveal them. Machine learning offers promise for improving detection, but it has limitations too. AI systems are only as good as their training data, and with only 3 confirmed interstellar objects, training data is scarce. There's a risk that AI might miss objects that don't match our expectations, or find false positives that waste observing time. The limitations of our detection methods have profound implications. If we're only seeing objects that pass close to the Sun, are relatively large, and happen to arrive when we're looking, what are we missing? The true population of interstellar objects might be vastly different from the biased sample we've observed. Some researchers estimate that for every interstellar object we detect, thousands pass through unnoticed. These invisible visitors might include objects that could answer our questions about their nature and origin. Perhaps perfectly preserved alien artifacts pass through the outer solar system regularly, but we'll never know because we can't see them. There are proposals to address these limitations. Space-based telescopes could observe continuously without atmospheric interference. Networks of small telescopes could provide all-sky coverage. Missions to the outer solar system could detect objects we can't see from Earth. But implementing these solutions requires resources, time, and political will. Until then, we're left with partial vision, seeing only the brightest needles in the cosmic haystack, trying to understand a phenomenon from the few examples that happen to pass through our narrow window of detection. Understanding these limitations is crucial for interpreting what we've found. When we say 3I/ATLAS showed anomalous behavior, we must remember that our observations were limited, our data incomplete. When we speculate about artificial origins, we must acknowledge how much we don't and can't know with current technology. The story of detecting interstellar objects is thus a story of human ingenuity pushing against fundamental limits. Each detection is a small miracle, a brief glimpse of something from impossibly far away, and each non-detection, each object that passes unseen, reminds us how much of the universe remains hidden from our view. Future missions and observations. The future of interstellar object research isn't just about waiting and watching. Scientists and engineers around the world are developing ambitious plans to intercept, study, and perhaps even sample these cosmic visitors. From ground-based observatories to interstellar missions, the coming decades promise revolutionary advances in our ability to understand objects like 3I/ATLS. The Vera Rubin Observatory, formerly the Large Synoptic Survey Telescope, will transform interstellar object detection when it begins operations. With its 8.4-meter mirror and 3.2 gigapixel camera, the largest digital camera ever built, it will photograph the entire visible sky every 3 nights. This unprecedented capability should detect dozens, perhaps hundreds of interstellar objects per year. But detection is just the beginning. The European Space Agency's Comet Interceptor mission, scheduled for launch in 2029, represents a new paradigm in space exploration. Instead of targeting a specific object, it will wait at the Sun-Earth-Lerth 2 Lagrange point, a gravitationally stable location about 1.5 million kilometers from Earth. When an interesting target appears, whether a pristine comet from our outer solar system or an interstellar visitor, the spacecraft will spring into action. Comet Interceptor consists of 3 modules that will separate as they approach their target, providing multiple perspectives and reducing the risk of total mission failure if one module is damaged by debris. The spacecraft will carry cameras, spectrometers, dust analyzers, and magnetometers, providing our first close-up look at an interstellar object if one passes within range. But Comet Interceptor has limitations. It can only reach objects that pass relatively close to Earth, and it has limited fuel for trajectory changes. Once committed to a target, there's no turning back. The mission gets one chance to choose wisely. More ambitious proposals are in development. The Interstellar Object Explorer, proposed by various research groups, would be a dedicated mission to chase down an interstellar visitor. Using high-efficiency ion propulsion or solar sails, it could potentially match velocities with an object like 3I/ATLS, allowing extended observation or even landing and sampling. Project Lyra, proposed by the Initiative for Interstellar Studies, outlines multiple mission architectures for reaching interstellar objects. These range from conventional chemical propulsion with gravitational assists to exotic concepts like laser-propelled light sails. Some scenarios could reach ʻOumuamua even now, decades after its discovery, though the journey would take decades more. The technical challenges are immense. Interstellar objects move at tens of kilometers per second relative to the Sun. Matching their velocity requires enormous energy, far beyond what current rockets can provide efficiently. Even reaching them for a brief flyby pushes our propulsion technology to its limits. But new technologies are emerging. Solar sails, which use radiation pressure from the Sun for propulsion, could achieve high velocities without fuel. The breakthrough Starshot project, though aimed at sending tiny probes to other star systems, is developing technologies that could be adapted for interstellar object missions. Electric propulsion, using ion or plasma thrusters, offers high efficiency that could enable long-duration chases. NASA's Psyche mission and other deep space missions are proving these technologies, paving the way for more ambitious applications. Nuclear propulsion, both fission and fusion, could provide the power needed to catch interstellar objects. While politically and technically challenging, nuclear rockets could achieve velocities impossible with chemical propulsion. DARPA's Draco program is working to demonstrate nuclear thermal propulsion in space. Ground-based observations will also advance dramatically. The extremely large telescope, under construction in Chile, will have a 39-meter mirror, dwarfing current telescopes. It will be able to study interstellar objects in unprecedented detail, potentially resolving surface features and detecting subtle compositional signatures. The Square Kilometre Array, a radio telescope being built in Australia and South Africa, will have unparalleled sensitivity for detecting radio emissions. If interstellar objects are transmitting signals, even weak ones, SKA, might detect them. Space-based telescopes offer unique advantages. The James Webb Space Telescope, though not designed specifically for interstellar objects, can provide infrared observations impossible from Earth. Future space telescopes could be positioned at Lagrange points or in solar orbit, providing continuous observation without atmospheric interference. Networks of small satellites could create a detection array covering the entire inner solar system. By coordinating observations from multiple positions, we could determine orbits more quickly and accurately, giving us more time to plan intercept missions. Artificial intelligence will play an increasing role. Machine learning algorithms are already being developed to identify potential interstellar objects in survey data. As we detect more objects and gather more data, these systems will become increasingly sophisticated at recognizing the subtle signatures of interstellar visitors. Citizen science projects allow amateur astronomers and enthusiasts to contribute to interstellar object research. Programs like Zooniverse enable volunteers to analyze telescope images, potentially discovering objects that automated systems miss. The amateur astronomer who discovered 2I/Borisov demonstrates the value of widespread participation. International cooperation will be essential. Interstellar objects don't respect national boundaries, and studying them requires resources beyond what any single country can provide. The International Astronomical Union has established protocols for naming and announcing interstellar object discoveries, but more coordination is needed for follow-up observations and potential missions. Private organizations are also entering the field. Breakthrough Listen, funded by billionaire Yuri Milner, has observed all known interstellar objects with radio telescopes. SpaceX and other commercial space companies could provide launch services for intercept missions. As costs decrease and capabilities increase, private missions to interstellar objects become feasible. Sample return missions represent the holy grail of interstellar object research. Bringing back material from another star system would revolutionize our understanding of planetary formation, stellar evolution, and potentially life itself. Japan's Hayabusa missions have demonstrated asteroid sample return, but applying this to fast-moving interstellar objects would be far more challenging. Some researchers propose stationing intercept vehicles at various locations in the solar system, ready to launch when an interstellar object is detected. This distributed approach would increase the chances of reaching objects with different trajectories, though the cost would be substantial. Long-term monitoring is also important. Even after an interstellar object becomes too faint for detailed study, tracking its position helps refine our understanding of its orbit and origin. Decades or centuries of observations could reveal subtle effects that short-term studies miss. The search for interstellar objects in historical data continues. As algorithms improve and more archives are digitized, we might discover that some objects previously classified as comets or asteroids were actually interstellar visitors. Each discovery would add to our understanding of their frequency and properties. Laboratory experiments complement observations. Scientists are creating analogs of proposed interstellar object compositions, studying how they would behave under space conditions. These experiments help interpret observations and test hypotheses about unusual properties like ʻOumuamua acceleration or 3I/ATLAS's fragmentation. Communication strategies are being developed for the possibility that an interstellar object responds to our signals or initiates contact. While this remains highly speculative, protocols for handling such a scenario are being discussed by scientists, ethicists, and policymakers. Public engagement will be crucial for maintaining support for these missions. The discovery of interstellar objects has captured public imagination in a way few astronomical phenomena do. Museums, planetariums, and educational programs are incorporating interstellar objects into their presentations, inspiring the next generation of scientists and explorers. Virtual reality and augmented reality technologies could allow people to visit interstellar objects, experiencing what it would be like to stand on 3I/ATLAS or fly alongside a phenomena. These immersive experiences could build public support for missions and research. As we look to the future, the questions raised by 3I/ATLAS and its companions drive innovation. Each proposed mission, each new telescope, each analytical technique brings us closer to understanding these mysterious visitors. Whether they're natural phenomena or something more, the quest to study them is pushing humanity's capabilities outward, preparing us for whatever discoveries await. The coming decades will likely see the detection of hundreds of interstellar objects, close encounters with a select few, and possibly the return of samples from another star system. Each discovery will add pieces to the puzzle, gradually revealing whether objects like 3I/AT-LAS are cosmic wanderers or cosmic messengers, random debris or deliberate probes, natural wonders or technological artifacts. Implications for life. The discovery of interstellar objects like 3I/AT-LAS forces us to confront profound questions about life in the universe. Not just whether life exists elsewhere, that seems increasingly likely given the vast number of planets, but how life might spread, communicate, and manifest across interstellar distances. These objects, whether natural or artificial, might be carriers, messengers, or evidence of biological processes we're only beginning to understand. Panspermia, the hypothesis that life can spread between planets and even star systems via meteoroids, asteroids, and comets, has gained renewed interest with the discovery of interstellar objects. If rocks can travel between stars, and if those rocks can carry organic molecules or even microorganisms, then life might not arise independently on each world, but could spread like seeds across the galaxy. 3I/AT-LAS and its companions provide potential vehicles for this process. Analysis showed they contained complex organic molecules, the building blocks of life as we know it. While these molecules can form through non-biological processes, their presence demonstrates that interstellar objects could deliver the raw materials for life to planetary systems. But could they deliver life itself? Microorganisms would face enormous challenges surviving interstellar journey, cosmic radiation, extreme cold, the vacuum of space, and timescales of millions of years. Yet we know that some Earth organisms, particularly bacterial spores and tardigrades, can survive remarkably harsh conditions, entering states of cryptobiosis, where metabolic processes essentially stop. Laboratory experiments have shown that some microorganisms can survive conditions simulating interstellar space, at least for limited periods. If embedded deep within a large object like 3I/AT-LAS, protected from the worst radiation, some organisms might conceivably survive the journey between stars. The implications are staggering. If panspermia occurs, life throughout the galaxy might be related, sharing common origins or at least common mechanisms. The discovery of life elsewhere might not reveal alien biochemistry, but cousin biochemistry, variations on themes that originated in some distant stellar nursery. This raises a disturbing possibility: contamination. If interstellar objects can carry life, then 3I/AT-LAS might have delivered alien microorganisms to our solar system. While the object didn't impact Earth, it shed dust and gas that could theoretically contain biological material. This material would be dispersed through the solar system, potentially reaching planets and moons. Conversely, material ejected from Earth by asteroid impacts could contaminate interstellar objects passing through our solar system. We might be inadvertently seeding the galaxy with terrestrial life, spreading our biological signature across the stars. But there's another dimension to consider: directed panspermia. This hypothesis, proposed by Francis Crick and Leslie Orgel, suggests that life might be deliberately spread by intelligent civilizations. Interstellar objects could be vehicles for this process, either carrying life directly or delivering the tools and information needed for life to arise. If 3I/AT-LAS or similar objects are artificial, they might be designed for biological purposes, not necessarily to deliver life to Earth. We already have that, but perhaps to sample it, study it, or influence its evolution. The object's apparent fragmentation could have released sampling devices or biological packages. This connects to broader questions about intelligence and technology. If civilizations can send probes between stars, they might use them for biological reconnaissance or even biological engineering on galactic scales. Each probe could be a mobile laboratory, analyzing the biochemistry of systems it passes through, perhaps even conducting experiments. The unusual chemical signatures of 3I/AT-LAS could be interpreted in this light. The complex organics, the unexpected isotope ratios, the thermal anomalies. Might these indicate biological processes or technologies we don't recognize? Could the object be a kind of living spacecraft, using biological systems for propulsion, computation, or self-repair? Extremophile research on Earth has expanded our concept of where life can exist. We've found organisms in boiling water, in solid rock, in radioactive environments, in places we once thought sterile. If life is this adaptable on Earth, What might be possible in the varied environments of interstellar space? Some researchers have proposed that interstellar objects themselves might be habitats, not dead rocks tumbling through space, but ecosystems adapted to interstellar conditions. They might harbor communities of organisms that feed on cosmic rays, magnetic fields, or quantum vacuum fluctuations, energy sources we're only beginning to understand. The timing of interstellar object discoveries raises interesting questions about Earth's biological history. Major evolutionary transitions, mass extinctions, and the emergence of new capabilities sometimes correlate with astronomical events. Could some of these correlations involve interstellar visitors we haven't yet recognized in the geological record? The Cambrian explosion, when complex multicellular life suddenly diversified about 540 million years ago, remains partially unexplained. Could an interstellar object have delivered new genetic material, catalysts, or environmental changes that triggered this evolutionary burst? It's highly speculative, but the possibility can't be entirely dismissed. Similarly, mass extinctions might not all be caused by asteroid impacts from within our solar system. An interstellar object striking Earth would be virtually indistinguishable from a solar system asteroid in the geological record, but it might carry different materials, different energies, different consequences. The emergence of intelligence itself raises questions. The rapid development of human cognitive abilities, the sudden appearance of symbolic thinking, the explosion of technological capability, these transitions happened quickly in evolutionary terms. While natural selection provides good explanations, the possibility of external influences, however remote, adds another dimension to consider. If interstellar objects can influence biological evolution, either accidentally or deliberately, then life's development isn't purely local. It's a galactic process, with information and material flowing between star systems, creating a vast network of biological exchange and evolution. This has implications for SETI, the search for extraterrestrial intelligence. Traditional SETI focuses on radio and optical signals, assuming civilizations communicate electromagnetically. But what if biology itself is the medium? What if intelligent civilizations communicate through designed organisms, genetic messages, or biological probes? 3I/Atlas's behavior could be interpreted through this lens. Its fragmentation might not be mechanical failure, but biological dispersal, like a dandelion releasing seeds. Its chemical emissions might carry information encoded in molecular structures. Its trajectory changes might be responses to biological or chemical gradients we haven't detected. The ethical implications are profound. If interstellar objects might carry life, how should we interact with them? Should we attempt to sample them, risking contamination in either direction? Should we deliberately target them with probes, potentially disrupting alien ecosystems or technologies? There's also the question of planetary protection. Current protocols focus on preventing contamination between Earth and other bodies in our solar system, but interstellar objects present new challenges. They arrive without warning, we can't sterilize them, and they might carry forms of life our protocols weren't designed to handle. Some researchers propose that Earth should develop detection and deflection capabilities specifically for interstellar objects that might pose biological risks. Others argue that the potential for learning about alien life outweighs the risks, especially given that such objects have likely been passing through our solar system throughout Earth's history. The discovery of interstellar objects also impacts our understanding of life's future. If life can spread between stars, either naturally or artificially, then life's long-term survival doesn't depend on any single star system. Even if our sun dies, Earth life might already have spread elsewhere, carried by ejecta from impacts or deliberately sent by future human civilizations. This cosmic perspective on life changes how we think about our responsibilities. If we're part of a galactic biological network, our actions have implications beyond Earth. The organisms we create, the genes we modify, the life we might destroy, these could have galactic consequences over geological timescales. Astrobiology missions now include interstellar objects in their planning. Future Mars sample return missions will look for evidence of material delivered by interstellar visitors. Missions to Europa and Enceladus will search for signs of panspermia in subsurface oceans. And direct missions to interstellar objects will prioritize biological sampling and containment. Laboratory studies continue to expand our understanding of life's limits and possibilities. Researchers are simulating interstellar conditions, testing whether organisms could survive journeys like that of 3I/ATL. They're also developing new techniques for detecting alien biochemistry that might not match our expectations. The field of xenobiology, the study of hypothetical alien life, has been energized by interstellar object discoveries. Researchers are exploring alternative biochemistries, silicon-based life, plasma-based organisms, quantum biology, and other exotic possibilities. If interstellar objects carry life, it might be unlike anything on Earth. Synthetic biology offers another angle. As we learn to design and create new forms of life, we might recognize signs of similar engineering in natural systems. The unusual properties of interstellar objects might make more sense when viewed through the lens of biological engineering rather than pure physics. The discovery of 3I/ATS and its companions has also influenced philosophy and theology. If life spreads between stars, are we less unique or more connected? If intelligence guides this process, what does that mean for our understanding of purpose and meaning? These questions, once purely philosophical, now have scientific dimensions. Public health organizations have begun considering scenarios involving alien organisms, however unlikely. While the risk is probably infinitesimal, the consequences could be severe. Protocols for handling potential alien biological material are being developed, drawing on experience with emerging diseases and planetary protection procedures. Education about interstellar objects increasingly includes biological dimensions. Students learn not just about orbits and compositions, but about panspermia, extremophiles, and the possibility that these objects might be more than sterile rocks. This prepares future scientists to think broadly about what interstellar visitors might represent. The connection between interstellar objects and life reminds us that astronomy and biology aren't separate sciences, but different perspectives on the same cosmic story. Every atom in our bodies, every gene in our cells, has a cosmic history. Some of that history might include journeys between stars, carried by objects like 3I/ATLS. As we continue to study interstellar visitors, each one adds data to our understanding of life's cosmic context. Whether they're sterile messengers or living arcs, random debris or engineered probes, they connect us to the broader galaxy in ways we're only beginning to appreciate. The silence paradox. If 3I/ATLS and objects like it are artificial probes sent by alien civilizations, we face an uncomfortable question: why the silence? No radio signals, no laser pulses, no obvious attempts at communication. These objects pass through our solar system, exhibit anomalous behavior that attracts our attention, and then leave without saying a word. This silence, in the context of potential artificiality, creates a paradox that reveals as much about us as it might about them. The Fermi paradox, the apparent contradiction between the high probability of alien civilizations and the lack of evidence for them, takes on new dimensions with interstellar objects. If these are probes, then aliens aren't absent, they're here, or at least their technology is, but they're not talking to us, at least not in ways we recognize. Several explanations have been proposed for this silence, each with different implications for the nature of these objects and their creators. The first possibility is that they're not trying to communicate at all. These might be purely observational probes, designed to gather data without interfering. Like wildlife cameras that record without disturbing, they might be programmed to remain undetected, or at least unobtrusive. The anomalies we observe might be unavoidable side effects of their operation, not attempts at contact. This raises questions about alien ethics and protocols. Perhaps there's a galactic equivalent of Star Trek's Prime Directive, a rule against interfering with developing civilizations. We might be under observation by probes that are specifically designed not to communicate until we reach some threshold of development. But what threshold? Radio technology, space travel, nuclear weapons, or something we haven't achieved yet, faster than light communication, artificial general intelligence, or some other capability we can't imagine. The silence might be telling us we're not ready, though ready for what remains unclear. Another possibility is that they are trying to communicate, but we don't recognize it. Communication requires shared context, shared symbols, shared understanding. An alien message might be encoded in ways that seem like noise to us. The brightness variations of 3I/ATLS that some interpreted as signals might actually be signals, just not in any format we understand. Consider how many ways information can be encoded: binary, analog, quantum states, chemical signatures, gravitational waves, neutrino beams, or methods we haven't discovered. The message might be in the trajectory, the rotation, the composition, the fragmentation pattern. We might be like ants examining a book, able to see the object, but unable to comprehend that the marks on its pages carry meaning. There's also the timescale problem. If these probes are millions of years old, their creators might be extinct, evolved beyond recognition, or simply no longer monitoring them. The probes might be faithfully transmitting to a civilization that no longer exists, or in formats that made sense millions of years ago but are obsolete now. The silence might also be deliberate but temporary. Perhaps the probes are programmed to remain quiet until they've completed their observations, analyzed their data, and determined the appropriate response. What seems like silence to us might be careful consideration by artificial intelligences trying to decide how to handle an unexpected situation. Some researchers have proposed that the silence is a test. By exhibiting anomalous behavior, but not communicating directly, the probes might be seeing how we respond. Do we investigate scientifically? Do we attempt communication? Do we attack? Our response might determine whether and how they eventually make contact. This connects to game theory and the zoo hypothesis. If the galaxy is full of intelligent civilizations, there might be established protocols for handling emerging species like us. The silence might be part of a larger strategy we don't understand, a move in a game whose rules we don't know. But there's a darker possibility. The silence might be protective, not for them, but for us. Direct contact with an advanced civilization could be culturally, technologically, or even biologically devastating. The silence might be kindness, giving us time to develop on our own before facing the reality of a populated galaxy. Or the protection might be for them. If these are probes from multiple civilizations, they might be maintaining silence to avoid revealing information to each other. The galaxy might be full of quiet watchers, each aware of the others, but unwilling to be the first to speak. The technological disparity could also explain the silence. If these probes represent technology millions of years ahead of ours, communication might be impossible, like trying to explain quantum mechanics to a bacterium. They might have concluded that meaningful dialogue is impossible until we advance further. Some scientists have suggested that the silence is actually information, that the absence of communication is itself the message. By demonstrating interstellar travel but not communicating, they might be telling us, this is possible, figure it out yourselves. It's teaching by example rather than instruction. The silence might also reflect uncertainty on their part. If these are artificial intelligences that have been traveling for millions of years, they might have evolved far from their original programming. They might be as puzzled by us as we are by them, unsure how to initiate contact or whether they should. There's also the possibility that communication is happening but not with us. The probes might be talking to each other, to other probes we haven't detected, or to Earth systems we don't recognize as recipients. They might be communicating with our computers, our satellites, or even biological systems in ways we haven't noticed. The quantum dimension adds another layer. If these civilizations have mastered quantum communication, their messages might be fundamentally undetectable by classical means. The silence we perceive might be because we're listening with the wrong physics. Cultural factors could play a role too. Perhaps silence is valued in galactic civilization. Perhaps communication is seen as crude or dangerous. Perhaps advanced civilizations have learned that silence is safer in a universe where not all intelligences are benign. The economic argument suggests that communication is expensive in terms of energy and risk. Why broadcast when you can observe quietly? Why reveal your capabilities to potential competitors? The silence might be strategic, maintaining advantage through obscurity. Some researchers have pointed out that our assumption that advanced civilizations would want to communicate might be anthropocentric. We're social beings who value communication, but intelligence might not always evolve that way. The silence might not be a choice, but a fundamental characteristic of most intelligence in the universe. The simulation hypothesis offers another angle. If our reality is simulated, the probes might be part of the simulation, programmed to exhibit certain behaviors, but not to communicate. The silence might be a limitation of the simulation, not a choice by the probes. As we develop our own interstellar probe concepts, we face similar decisions. Should our probes announce themselves to any civilizations they encounter? Should they remain silent until certain conditions are met? Should they communicate with Earth about their discoveries, potentially revealing our location to eavesdroppers? The silence of 3I/ATLS and similar objects might be teaching us about our own future. When we send probes to other stars, we might choose silence for the same reasons these objects do. The paradox might resolve not through contact, but through understanding why contact doesn't happen. Yet the silence isn't complete. The objects themselves are a form of communication, even if unintentional. Their existence tells us that interstellar travel is possible. Their anomalies hint at technologies we haven't developed. Their trajectories might encode information about their origins or destinations. As our detection and analysis capabilities improve, we might discover that the silence wasn't silence at all, but a signal we couldn't perceive. Future observations of interstellar objects might reveal patterns, messages, or behaviors that transform our understanding of what we thought was quiet passage. The silence paradox ultimately reflects our limitations as much as their choices. We're listening with primitive instruments for signals we might not recognize, from beings whose motivations we can't fathom, using physics we might not understand. The silence might not be empty but full of information we're not yet equipped to receive. Global response and policy. The discovery of 3I/Atlas and its peculiar characteristics triggered responses not just from the scientific community, but from governments, international organizations, and the public worldwide. How humanity collectively responds to potential evidence of alien technology reveals much about our readiness for contact and our ability to cooperate on issues that transcend national boundaries. Within hours of 3I/Atlas being confirmed as interstellar, classified briefings were reportedly held in major capitals. While most of these discussions remain secret, leaked documents suggest that defense and intelligence agencies took the discovery seriously, particularly given the anomalies that emerged as observations continued. The United Nations Office for Outer Space Affairs, UNOSA, convened an emergency session to discuss protocols for dealing with interstellar objects. While UNOSA had existing guidelines for potentially hazardous asteroids, interstellar visitors presented new challenges. They moved faster, were harder to predict, and raised the possibility, however remote, of artificial origin. The Committee on the Peaceful Uses of Outer Space drafted new recommendations for international cooperation in observing and studying interstellar objects. These included protocols for data sharing, coordinated observations, and decision-making processes for potential intercept missions. However, the recommendations were non-binding, and several nations reserved the right to act unilaterally if their security interests were threatened. NASA and the European Space Agency immediately began adjusting their observation priorities, dedicating more telescope time to tracking 3I/ATLS. The Chinese National Space Administration and the Russian space agency Roscosmos similarly redirected resources, though they were less transparent about their activities. The military implications weren't ignored. The US Space Force and equivalent organizations in other countries assessed whether interstellar objects could pose threats, either directly through impact or indirectly if they were surveillance devices from rival nations disguised as natural phenomena. While no evidence supported these concerns, the possibility couldn't be entirely dismissed. More intriguingly, several nations reportedly discussed the possibility of capturing or intercepting future interstellar objects. The technological and scientific advantages of obtaining material or technology from another star system would be enormous. This raised concerns about a potential interstellar object race, with nations competing to be first to retrieve and potentially reverse engineer alien technology. International law proved inadequate for addressing these scenarios. The Outer Space Treaty of 1967 prohibits nations from claiming sovereignty over celestial bodies, but does it apply to objects passing through our solar system? If an interstellar object is artificial, who has the right to study or claim it? These questions exposed gaps in our legal frameworks for dealing with truly novel situations. The scientific community attempted to maintain international cooperation despite political tensions. The International Astronomical Union established working groups specifically for interstellar objects, creating standardized protocols for observation, naming, and data sharing. Scientists emphasized that understanding these objects required global cooperation, as no single nation had all the necessary capabilities. However, not all data was shared freely. Some observations, particularly those that might indicate artificial origin or advanced technology, were classified by various governments. This created a two-tier system where public science proceeded with incomplete information, while classified research potentially reached different conclusions. The private sector also responded to the discoveries. Space companies like SpaceX, Blue Origin, and others began developing mission concepts for intercepting interstellar objects. Venture capitalists funded startups focused on detecting and analyzing these visitors. The potential commercial value of alien technology, however speculative, attracted significant investment. Insurance companies faced novel questions. If an interstellar object damaged satellites or posed risks to Earth, who was liable? How should policies account for risks that were literally astronomical in origin? New categories of coverage were developed for interstellar events, though premiums were largely guesswork. Public reaction varied widely across cultures and nations. In some countries, the discovery reinforced existing beliefs about humanity's special place in the universe. In others, it challenged religious and philosophical worldviews. Education systems struggled to incorporate rapidly evolving science into curricula. The media played a crucial role in shaping public perception. Initial coverage was often sensationalized, with headlines proclaiming alien probe visits solar system based on limited evidence. More responsible outlets tried to convey the uncertainty and complexity of the observations, but nuanced messages often lost out to dramatic narratives. Social media amplified both reasonable discussion and wild speculation. Conspiracy theories flourished, claiming governments were hiding evidence of alien contact, or that the objects were secret military projects. Fact-checkers struggled to address claims that mixed real observations with unfounded speculation. Religious organizations offered varying interpretations. Some saw interstellar objects as part of divine creation, others as challenges to human uniqueness. The Vatican Observatory, one of the oldest astronomical institutions, hosted conferences on the theological implications of potential alien technology. Indigenous communities offered unique perspectives, often overlooked in mainstream discourse. Some pointed to traditional knowledge about visitors from the stars, suggesting that interstellar objects might have been observed and recorded in oral histories. While these connections were often tenuous, they highlighted different ways of understanding cosmic phenomena. The discovery influenced policy decisions beyond space. Climate change negotiations referenced the possibility of alien civilizations as a reason for either hope, advanced technology might offer solutions, or urgency, we need to survive long enough to make contact. Defense budgets included line items for anomalous aerospace phenomena, a euphemism for potential alien technology. International scientific collaborations were both strengthened and strained. Projects like the Square Kilometre Array and the Extremely Large Telescope received increased funding as nations recognized their importance for studying interstellar objects. But competition for observation time and concerns about data sharing created tensions. The World Health Organization quietly developed protocols for potential biological contamination from interstellar objects. While the risk was considered minuscule, the consequences of alien microorganisms reaching Earth were potentially severe enough to warrant preparation. Economic modeling attempted to quantify the impact of confirming alien technology. Stock markets showed volatility when new observations were announced. Some sectors, particularly aerospace and defense, saw increased investment. Others worried about technological disruption if alien technology made existing industries obsolete. Educational initiatives proliferated. Universities created new programs in astrobiology and interstellar studies. Museums developed exhibitions about interstellar visitors. Citizen science projects engaged millions in searching for and analyzing potential interstellar objects. The long-term policy implications are still unfolding. Some advocate for a planetary defense force capable of intercepting and studying interstellar objects. Others propose international treaties, specifically addressing alien technology and contact protocols. Still others argue for maintaining scientific openness despite security concerns. The discovery of 3I/Atlas has forced humanity to confront governance challenges we're not prepared for. How do we make collective decisions about phenomena that affect all of humanity? How do we balance scientific openness with security concerns? How do we prepare for possibilities that seem remote but would be transformative if they occurred? These questions extend beyond interstellar objects to broader issues of global governance in an age of rapid technological change. The response to 3I/ATLS might be a rehearsal for future challenges: asteroid mining, genetic engineering, artificial intelligence, or actual contact with alien civilizations. As more interstellar objects are discovered, these policy challenges will become more urgent. Each visitor forces us to refine our protocols, improve our cooperation, and confront the possibility that we're not alone. Whether these objects are natural or artificial, they're already changing how humanity thinks about itself and its future. The global response to 3I/ATLAS reveals both our potential for cooperation and our persistent divisions. We're capable of coming together to study these cosmic visitors, but we're also prone to competition, secrecy, and conflict. How we resolve these tensions might determine not just our understanding of interstellar objects, but our readiness for whatever comes next. Personal reflections. Sometimes, in the quiet hours when the data analysis is done and the telescope time has ended, scientists allow themselves to feel the full weight of what they're studying. 3I/ATLAS isn't just a collection of observations and anomalies. It's a visitor from another star, a fragment of somewhere else that briefly entered our lives and left us with more questions than answers. I think about the astronomers who first spotted that faint smudge of light, not knowing they were about to discover something that would challenge our understanding of what moves between the stars. The excitement of those first calculations, confirming the hyperbolic orbit, realizing this was only the third interstellar object ever detected. The late nights trying to squeeze every possible observation from telescopes around the world before the object faded from view. There's something profoundly humbling about studying interstellar objects. We're examining something that has traveled for possibly millions of years, across distances we can barely comprehend, carrying secrets from a place we'll never see. Every photon of light reflected from 3I/ATLAS had a story to tell, if only we knew how to read it. The human dimension of this research often gets lost in the technical papers and statistical analyses. But behind every observation is a person who chose to spend their night looking at a tiny point of light, hoping to learn something new. Graduate students who devoted years to developing better detection algorithms. Technicians who maintained the telescopes through freezing nights and equipment failures. Administrators who fought for funding and telescope time. The debates about 3I/ATLAS's nature weren't just academic exercises. They were passionate discussions among people who deeply care about understanding our place in the universe. The researcher who spent months analyzing spectral lines, convinced they'd found evidence of unusual chemistry. The dynamicist who modeled thousands of possible trajectories, trying to explain those tiny anomalies. The theorist who dared to suggest, despite potential ridicule, that maybe, just maybe, this wasn't entirely natural. Working on interstellar objects changes you. It expands your perspective in ways that are hard to describe to those who haven't experienced it. You start thinking in astronomical units and light years. You become comfortable with uncertainty, with questions that might never be answered. You learn to hold multiple possibilities in your mind simultaneously. It could be natural, it could be artificial, it could be something we haven't imagined. The loneliness of the work is real. Most nights, you're alone with the data, trying to extract meaning from numbers and images. The object itself is impossibly distant, already far beyond our reach by the time we truly understand what we've seen. There's no possibility of a second look, no chance to verify our interpretations with additional observations. We get one chance, and then it's gone forever. But there's also a profound sense of connection to colleagues around the world working on the same puzzles. Connection to the generations of astronomers who wondered about visitors from other stars before we had the tools to detect them. And strangest of all, potential connection to whoever or whatever sent these objects our way, if indeed anyone did. The possibility that 3I/ATLAS might be artificial adds an emotional dimension that's hard to convey. Every anomaly might be a message. Every unusual characteristic might be intentional. You find yourself wondering, are we being watched? Are we being tested? Are we missing something obvious that a more advanced civilization would expect us to see? These thoughts come especially at night, when you're alone at the telescope or staring at data on a screen. The universe feels very large and very quiet. The idea that something intelligent might have sent 3I/ATLAS makes you feel both less alone and more isolated. Less alone because it would mean other minds exist out there. More isolated because they're not talking to us, at least not in ways we understand. The responsibility weighs on you too. If these objects are artificial, then how we study them, how we interpret them, how we respond to them, might be the most important work our species has ever done. First contact, if that's what this is, won't be dramatic like in the movies. It will be gradual, uncertain, revealed through careful analysis of subtle anomalies, and we might be the ones doing that analysis. There's also frustration. So many questions we can't answer, so many observations we couldn't make. If only we detected 3I/ATLAS earlier. If only we had better instruments. If only we could send a probe to intercept it. The limitations of our technology and our brief window of observation are maddening when you're trying to solve possibly the greatest mystery humanity has ever faced. The public attention is both gratifying and challenging. It's wonderful that people care about interstellar objects, that they're excited by the possibility of alien technology. But the pressure to provide definitive answers when the data is ambiguous, the tendency of media to sensationalize uncertain results, the conspiracy theories that spring up around classified observations, these complicate an already difficult job. Working on 3I/ATLAS has made me think differently about Earth and humanity. We're on a pale blue dot, circling an ordinary star, in an unremarkable corner of the galaxy. Yet we're capable of detecting and studying objects from other star systems. We're asking questions that our ancestors couldn't even formulate. We're possibly on the verge of the greatest discovery in human history. But we're also fragile. Our observations of 3I/ATLAS were limited by weather, by equipment failures, by funding constraints, by human conflicts. A cloudy night at a critical telescope meant lost data. A government shutdown delayed observations. The COVID pandemic restricted access to observatories. We're trying to understand cosmic mysteries while dealing with very human limitations. The international collaboration required to study interstellar objects gives me hope. Despite political tensions, scientists from different nations shared data, coordinated observations, and worked together to understand these visitors. When faced with something truly beyond our world, we're capable of transcending our divisions, at least temporarily. But the secrecy and competition worry me. Classified observations that aren't shared with the scientific community. Nations planning unilateral missions to intercept future objects. The possibility that the discovery of alien technology could spark conflict rather than cooperation. We're not yet mature enough as a species to handle some of what we might discover. Personal moments stand out amid the scientific work. The night I first saw 3I/ATLAS through a telescope, a tiny dot of light that had traveled from another star. The morning we received spectroscopic data showing those unusual chemical signatures. The afternoon we realized the trajectory anomalies couldn't be explained by standard models. Each discovery felt like opening a door to a room we didn't know existed. The dreams are vivid. Sometimes I dream about what 3I/ATLAS really is. A probe covered in ice, its alien machinery hidden beneath. A fragment of a destroyed planet, carrying fossils of creatures we can't imagine. A message in a bottle, thrown into the cosmic ocean by a civilization seeking contact. Or just a weird comet, unusual but ultimately natural, and we're reading too much into random variations. The impact on my worldview has been profound. I can no longer look at the night sky without wondering what's passing through unseen. Every star might have planets that have sent objects our way. Every point of light might be not just a star, but a home to intelligence that has already found us, in a sense, by sending their emissaries, intentional or otherwise. The question of meaning haunts me. If 3I/ATLAS is artificial, what does that mean for humanity? Are we significant because we detected it, or insignificant because we can barely understand it? If it's natural, does that make us more alone or more connected to natural processes that operate throughout the galaxy? As I write this, 3I/ATLAS continues its journey into interstellar space, growing fainter and more distant every day. Soon it will be beyond the reach of any telescope we possess, but its impact remains. The questions it raised, the possibilities it suggested, the reminder that our solar system isn't isolated, but part of a vast interconnected galaxy where objects and perhaps information flow between the stars. Working on 3I/ATLAS has been the privilege of a lifetime. To be among the first humans to study confirmed interstellar objects, to contribute, however slightly, to our understanding of these cosmic visitors, to be part of the generation that discovered we're not gravitationally alone, objects from other stars do reach us. But it's also been humbling. We know so little. We understand even less. We're like children on a beach, finding shells and wondering about the ocean. 3I/ATLS was one shell, beautiful and mysterious. There will be others. Each one will teach us something new, raise new questions, challenge our assumptions. The continuing mystery. As 3I/Atlas fades into the darkness between stars, growing dimmer each night until even our most powerful telescopes can no longer detect it, we're left with a mystery that refuses to resolve into simple answers. The object came, we observed. It left, and in between, it challenged nearly everything we thought we knew about what travels through interstellar space. The data we collected tells a story, but it's a story with missing pages, ambiguous passages, and an ending we'll never read. The chemical signatures that didn't quite match our expectations, the brightness variations that might have been signals or might have been chaos, the trajectory that followed the laws of physics, but with subtle deviations that those laws couldn't quite explain. Each anomaly is a thread, and we're not sure if they weave together into a pattern, or if we're seeing patterns where none exist. Science usually progresses through convergent evidence, multiple observations, repeated experiments, independent confirmations that gradually build toward consensus. But with 3I/ATLS, we had one chance, limited observations, and no possibility of repetition. We're trying to solve a puzzle with most of the pieces missing, and no picture on the box to guide us. The competing hypotheses remain unresolved. Was it a fragment of nitrogen ice from an exoplanet, exhibiting strange properties because of its unusual composition? Was it a hydrogen iceberg, invisible to most of our instruments, but capable of producing the observed acceleration? Was it a dust bunny, a fractal aggregate of particles that behaved unlike anything in our solar system? Or was it something else entirely, something that doesn't fit our categories of natural objects? Each explanation has its advocates and its critics. The nitrogen ice hypothesis explains some observations, but requires very specific conditions that might be rare. The hydrogen iceberg theory works mathematically, but has never been observed in nature. The dust bunny model matches some characteristics, but not others. And always lurking at the edges of scientific discussion is the possibility that none of our natural explanations are correct, because 3I/ATLS wasn't entirely natural. The artificial hypothesis remains neither proven nor disproven. The accumulation of anomalies is suggestive, but not conclusive. The lack of obvious artificial signals or structures argues against it, but our ideas about what artificial should look like might be wrong. We're left in an uncomfortable middle ground where we can't dismiss the possibility, but can't confirm it either. This uncertainty extends to the bigger picture. If we've detected 3 interstellar objects in as many years, how many more are out there? Are they common, with thousands passing through our solar system at any given time? Or are we in a special moment, perhaps passing through a stream of objects ejected from some distant system? The statistics of small numbers don't allow firm conclusions. The diversity among the 3 known interstellar objects raises its own questions. Why was ʻOumuamua so weird, Borisov so normal, and 3I/ATLS somewhere in between? Does this reflect natural variation in a phenomenon we don't understand, or are we seeing different categories of objects with different origins and purposes? With only 3 examples, we can't even define what's typical. Our detection capabilities are improving rapidly. New telescopes, better algorithms, more comprehensive surveys. We'll almost certainly detect more interstellar objects in the coming years. Each one will add data to our understanding, but will more data resolve the mystery or deepen it? Will we find obvious artificial probes that settle the question, clearly natural objects that explain all anomalies, or more ambiguous visitors that sustain the uncertainty? The planned missions to intercept future interstellar objects offer hope for more definitive answers. Actually visiting one of these cosmic travelers, sampling its material, studying it up close, would provide data that remote observation never could. But these missions face enormous technical challenges and will take years or decades to implement, and they'll only study new objects, not the ones we've already lost to the darkness. There's also the sobering possibility that we've already missed the most interesting visitors. How many interstellar objects passed through before we had the capability to detect them? Did obviously artificial probes visit our solar system centuries or millennia ago, observed as comets or meteors by our ancestors who had no framework for understanding their true nature? The historical record might contain descriptions of interstellar visitors misinterpreted as divine signs or natural phenomena. Looking forward, the mystery of 3I/ATLs will likely persist for years, perhaps decades. New theoretical models might explain its anomalies naturally. Observations of similar objects might establish patterns that make its behavior seem normal, or future discoveries might make its potentially artificial nature more plausible or even obvious in hindsight. The mystery extends beyond the scientific to the philosophical. What does it mean that objects from other stars can reach us? How does this change our understanding of our solar system as not isolated but connected to the galaxy? If some of these objects are artificial, what does that say about intelligence and technology on cosmic scales? Even if they're all natural, what does their diversity tell us about the processes operating in other star systems? The cultural impact of the mystery continues to grow. 3I/ATLAS and its companions have entered our collective consciousness as symbols of the unknown, the alien, the possible. They've inspired art, literature, music, and countless discussions about our place in the universe. The mystery has value beyond its scientific importance. It reminds us that the universe still holds surprises, that discovery is possible, that wonder isn't obsolete. For the scientists who studied 3I/Atlas, the mystery is both frustrating and exhilarating. Frustrating because we may never know what it really was. Exhilarating because we're privileged to be asking questions that couldn't even be formulated a generation ago. We're the first humans to confirm that objects from other stars visit our solar system, even if we don't fully understand what they are. The continuing mystery also serves as a humility check for our species. We've split the atom, decoded the genome, sent probes to the edge of our solar system, but we can't definitively explain a chunk of ice and rock that happened to pass by. It reminds us that for all our achievements, we're still beginners in understanding the cosmos. There's something poetic about the mystery's persistence. 3I/ATLAS came from darkness and returned to darkness, briefly illuminated by our sun and our attention. We'll never see it again, never have another chance to study it. It's becoming a legend even as it remains a scientific puzzle, a visitor that raised questions we couldn't answer before disappearing forever. The mystery connects us to future generations who will have better tools, deeper understanding, more complete data. They might look back at our observations of 3I/ATLAS and see something obvious that we missed, or they might marvel that with such limited data, we came so close to the truth, or they might find that the mystery has only deepened with time, that 3I/ATLAS was even stranger than we imagined. In a sense, the continuing mystery is a gift. It keeps us looking, wondering, questioning. It prevents us from becoming complacent, from thinking we understand everything about our cosmic neighborhood. It reminds us that the universe is vast, ancient, and full of phenomena we haven't even imagined yet. As I contemplate the mystery of 3I/ATLAS, I'm reminded of how science really works, not through sudden revelations or dramatic discoveries, but through patient accumulation of evidence, careful analysis of anomalies, and the gradual expansion of our understanding. The mystery isn't a failure of science, but science in action, the process of trying to understand something genuinely new with tools and concepts developed for other purposes. The mystery also highlights the importance of keeping an open mind while maintaining scientific rigor. We can't jump to conclusions about alien technology based on ambiguous evidence, but we also can't dismiss possibilities just because they seem unlikely. The history of science is full of unlikely things that turned out to be true. Conclusion: what lies beyond? And so we come to the end of our journey with 3I/Atlas, though in truth, the journey has no real ending. The object continues its voyage through interstellar space, carrying its secrets into the darkness between stars. We continue our watch, scanning the skies for the next visitor, the next mystery, the next piece of this vast cosmic puzzle. What have we learned from 3I/ATA? That our solar system is not isolated, but connected to the galaxy through a constant exchange of material, that objects from other stars can reach us, have reached us, will continue to reach us, that these visitors can be stranger than we expected, exhibiting properties and behaviors that challenge our understanding of what's possible. We've learned that detecting interstellar objects is difficult but not impossible, that studying them requires international cooperation, rapid response, and acceptance of uncertainty, that even with our best efforts, we can only glimpse these cosmic travelers briefly before they disappear forever. Most importantly, we've learned that we don't have all the answers. 3I/ATA, Alice presented us with anomalies we couldn't fully explain, patterns we couldn't completely decode, questions we couldn't definitively answer. It reminded us that the universe is still capable of surprising us, that there are phenomena beyond our current understanding. That mystery is not a relic of pre-scientific thinking, but a driving force of scientific progress. The question posed at the beginning, what if 3I/Atlas wasn't what we think, remains open. Maybe it was exactly what we think, a strange but ultimately natural fragment from another star system. Maybe it was something more, a probe, a message, a piece of technology we don't recognize. Maybe it was something in between, a natural object modified by intelligence, or an artificial object designed to appear natural. The beauty is that we don't know, and that not knowing drives us forward. It motivates new observations, new theories, new missions. It inspires young scientists to enter the field, bringing fresh perspectives and ideas. It captures public imagination, generating support for the research needed to answer these cosmic questions. As you lie there in the darkness, perhaps looking up at the stars, consider that right now, at this very moment, interstellar objects are passing through our solar system. Most are too small or too distant for us to detect, but they're there, silent travelers carrying stories from other stars, other systems, perhaps other civilizations. Some might be ancient beyond imagination, older than our solar system, older than Earth itself. They've witnessed the birth and death of stars, the formation of planets, possibly the rise and fall of civilizations. They're libraries of cosmic history, if only we knew how to read them. Others might be young, recently ejected from their home systems, beginning journeys that will last longer than species, longer than worlds. Where 3I/Atlas is now, where it will be in a million years, what stars it might visit, what other curious minds might observe it and wonder about its origin. These are stories we'll never know but can imagine. The search continues. Tonight, tomorrow, every clear night, telescopes around the world and in space scan the skies. Computers analyze millions of images, looking for the telltale motion that indicates something doesn't belong, something has come from elsewhere. Most of what they find will be asteroids, comets, cosmic dust from our own system. But occasionally, rarely, magnificently, they'll find another visitor. When that happens, and it will happen, we'll be ready. Better instruments, refined techniques, prepared protocols. Each interstellar object we discover teaches us how to better study the next one. We're learning the language of these cosmic messengers, even if we don't yet understand what they're saying. The possibility that some of these objects might be artificial adds a profound dimension to our watch. We're not just doing astronomy, we might be doing archaeology, studying the artifacts of civilizations we've never met. We're not just observing, we might be participating in a galactic community we don't yet recognize. But even if every interstellar object turns out to be natural, their study transforms our perspective. They connect us to the galaxy in a tangible way. They show us that the space between stars isn't empty, but populated with wanderers, outcasts, messengers. They remind us that our solar system is part of a larger story, one that began before our sun formed and will continue after it dies. 3I/Atlas challenged us to think bigger, to question our assumptions, to consider possibilities we might otherwise dismiss. It showed us that the universe is still full of mysteries, that discovery is not a thing of the past but an ongoing adventure. It reminded us that we're still at the beginning of our understanding, still children learning to read the cosmic signs. As you drift towards sleep, perhaps you'll dream of 3I/Atlas, not as a cold chunk of ice and rock tumbling through space, but as something more, a messenger from distant stars, a puzzle waiting to be solved, a reminder that the universe is vast and strange and wonderful beyond our current imagination. Dream of the civilizations that might have sent it, if indeed any did. Dream of the worlds it might have come from, the suns it might have circled before beginning its interstellar journey. Dream of the future observers who might detect it eons from now, wondering as we wonder about its nature and origin. And when you wake, remember that the mystery continues, that somewhere out there, beyond the edge of detection, beyond the reach of our telescopes, objects from other stars are approaching. Some might be ordinary, some might be extraordinary, some might carry answers to questions we haven't thought to ask. The story of 3I/Atlas is not ending but beginning. It's the first chapter in humanity's study of interstellar visitors. the opening notes of a symphony we're just learning to hear. Each new discovery will add to the melody, building toward an understanding we can only imagine. What if 3i/ATLAS wasn't what we think? The question remains open, inviting, profound. It challenges us to keep watching, keep wondering, keep reaching toward the stars. It reminds us that the greatest discoveries often come not from finding answers, but from finding better questions. In the end, 3i/ATLAS gave us exactly what we needed. Not certainty, but curiosity. Not answers, but wonder. Not conclusion, but continuation. It showed us that our cosmic story is still being written, that new chapters await, that the universe has barely begun to reveal its secrets. The object itself is gone now, too faint for any telescope, too distant for any probe we could send. But its legacy remains in the data we collected, the questions it raised, the imagination it sparked. Every future interstellar object will be compared to it. Every anomaly will recall its mysteries. Every possibility will echo its potential. Somewhere in the darkness between stars, 3i/ATLAS continues its eternal journey. It carries with it the light of our sun, reflected however briefly from its surface. It carries the gravity of our planets, their subtle influences on its trajectory. And in a poetic sense, it carries our wonder, our questions, our hope that the universe holds more than we've dreamed. As this documentary draws to a close, as your eyes grow heavy and sleep approaches, know that the mystery lives on. Tomorrow, new observations. Next year, new discoveries. Next decade, perhaps answers to questions that seem impossible today, or perhaps new questions we haven't imagined. New mysteries that make today's puzzles seem simple. The universe is patient with its revelations. It doesn't rush to satisfy our curiosity. It reveals itself slowly, in glimpses and hints, in anomalies and wonders. 3i/ATLAS was one such glimpse, a brief window into the complexity and mystery of what moves between the stars. What if it wasn't what we think? What if none of them are what we think? What if the universe is stranger, more alive, more connected than we've dared to imagine? These questions don't have answers yet, but they have power. The power to drive discovery, to inspire wonder, to keep us looking up and asking why. And that perhaps is the greatest gift 3i/ATLAS gave us. Not answers, but better questions. Not certainty, but deeper mystery. Not an ending, but a beginning. The beginning of humanity's true engagement with the interstellar, with the cosmic, with the vast darkness that holds more light than we've yet learned to see. Sleep well, fellow traveler on this small world, orbiting this ordinary star, in this unremarkable corner of the galaxy. But sleep knowing that remarkable things pass our way, that mysteries await solution, that wonders await discovery, that somewhere out there, perhaps closer than we think, answers to our deepest questions drift silently through the cosmic dark. The story of 3i/ATLAS ends here, but only for tonight. Tomorrow the search continues. Tomorrow new data arrives. Tomorrow we might detect another visitor, another mystery, another piece of the vast puzzle of existence. And maybe, just maybe, tomorrow we'll understand what today seems impossible. Until then, we watch, we wonder, we wait, and we remember that in a universe vast beyond comprehension, ancient beyond measure, and strange beyond imagination, anything is possible. Even the possibility that a chunk of ice and rock named 3i/ATLAS was something more than we dared to believe. The cosmos doesn't promise us answers. It promises us questions worth asking. And in that promise, in that endless invitation to wonder, we find not just the story of 3i/ATLAS, but the story of ourselves, curious minds on a tiny world, reaching toward infinity, finding meaning in mystery, and discovering that the journey itself is the destination. Good night, and may your dreams be filled with interstellar wonders, cosmic mysteries, and the quiet certainty that somewhere out there, something extraordinary is heading our way. We just have to keep watching. Keep wondering, keep believing that the universe has secrets yet to share, and that we, against all odds, might be the ones to discover them. The darkness between stars isn't empty. It's full of possibilities, full of wanderers, full of stories waiting to be told. 3i/ATLAS was one story, brief and mysterious, profound and unfinished. But it won't be the last. The universe has more to show us, more to teach us, more to challenge us with, and so we end where we began, with a question that opens rather than closes. that invites rather than concludes. What if 3i/Atlas wasn't what we think? The answer, like the object itself, drifts somewhere in the darkness, waiting to be found.